Then we can start.
Okay, Stephen, I will make you the co-host so you can also admit people.
Carsten, I think you can start.
Okay.
Is it live now?
Yeah, we are live.
Okay. Well, good morning, good afternoon, and good evening to everyone from whichever part of the planet you're joining today. We happily welcome you to this meeting and appreciate your enthusiasm to join us despite the situation around the world. And yeah, some places the sun might not have risen yet, and at some places it might have gone down already. But I think we are ready to start now this meeting on eddies and internal waves, flow decomposition and parameterizations. So today is the first day of the meeting, and Carsten will now give an introduction to TRR 181 and its framework. I just want to introduce a couple of instructions that you should keep in mind during the meeting. Since we are a lot of people, please mute your microphones and preferably also cameras during the meeting. Yeah, and when we are talking, we have discussions, then you can also choose to turn on your camera as you please. Please turn off your cameras and mics during breaks. And when you have to ask questions, you can type it in the chat. The session moderators will read it at the end of each talk. If there's not enough time during the discussion time after the talks, we have a longer discussion period at the end where we can take these questions. We also have live question and answer session outside outside Zoom. So Stephen or I will relay the questions to the moderators, and any questions which are not taken during the talks can be taken at the discussion. And please explore Gather Town, which we have set up for social and scientific interactions. And if anything you are not able to discuss during the meeting, you can always discuss at Gather Town. And as you all know, the meeting is also streamed live. So you can also watch it there if there are issues for you entering the Zoom room. Yeah, I think that is it. The live stream will remain at the same link available even after today's session, so you can watch it also later. Yeah, and we wish you a nice experience at the workshop. Carsten, I think you can continue now.
Okay, thanks, Manita, for this introduction. Actually, my name is Carsten Ehn, for those who don't know me, but the organizer is actually Manita. And we are both, and also many others, are part of this Transregio energy transfers in atmosphere and ocean with this number 181, which you might have heard about, which I want to introduce a little bit in the next couple of minutes, in case you don't know what we are doing. And so this is here our starting point of this project. It's like that we found that the energetics of closures, which we usually use in climate models or in ocean and atmosphere models, are usually inconsistent in the way that energies are dissipated, for instance, by parameterizations, and then lost and at other places put into these models again. So that's what we mean by inconsistent. And that's, of course, related to missing understanding. And we actually identified the most important dynamic regimes as waves and Rossby waves, gravity waves and Rossby waves, and the interaction between them as the most important thing which hampers this consistent energetics in climate models. And then, of course, it's also accompanied by inconsistent numerics in the models. You all know about the problems in the abstraction schemes, but also mathematical theory. We actually don't know about the mathematics of existence and of solutions and convergence of our equations to the real world, actually. So these are all problems which we have identified and which we want to tackle to improve climate models. And this is actually, the slide which you see is actually from a review for our first phase of the project, which we had in, or which we didn't have because of Corona last spring. And we wanted to advertise a little bit the benefits which you get from improving the energetics of models. And you will also see this later by the talk by Stefan Juricke. He has implemented eddy backscatter in a comprehensive ocean model, actually in the FESOM model from Bremerhaven, and showed that it actually improves the model. So if you put in some energetically more consistent closures, it's not completely consistent, but at least more consistent into ocean models, it improves. And what you see here is the ratio of the simulated sea surface height variability to the observed one in the reference simulation on the left, and in the improved model with eddy backscatter on the right. And you see the red is bad, blue is also red, but white is good, and it's more white on the right hand side. So it's improving our models. And this has been done already in the first phase, the first 4 years of our project. Also other things, we're also working in the atmosphere. What you see here is a similar study doing this similar thing also in the atmosphere, in an atmosphere model, but using also stochastic elements in energy backscatter. And what you see is wave number spectrum of the variability in this atmosphere model. And you'll see that having coarse resolution models with the closure brings a better agreement with high resolution models than without the closure, which is these dashed lines. So there's improvement from this here paper co-authored by our PI Christian Franzke, which you might know. He recently went to South Korea, actually, to Busan, to the Climate Institute there. And so this is one thing which we advertised during that review session to defend our project. And of course, there are also other things like publications, of course, we have to publish. And what we also do is, of course, we implement the parameterizations which we have, like IDMix, that's gravity wave closure, AIL, that's about vertical coordinates. They are implemented in 2 climate models, which we are focusing on in this project. And they are both, at least the ocean parts are both related, discretized on unstructured grids. And that's OpenIFS, FESOM from Bremerhaven, from AVI, and ICON Atmosphere Ocean from MPIM. And what you see here is a schematic of the energy transfers in this MPI model with different closures. And you see the arrows here between the different compartments in terms of terawatts of energies. But this model is not completely consistent yet. You see these red arrows. They are missing, actually, energy transfers which are not closed. But at least we know a little bit better about the energy transfers in that model, and we can improve. We're also focusing on observations in the ocean, in the atmosphere. There's an example here from Mark Buckley, where he first time observed actually the atmospheric flow close to the sea surface, and the waves actually are introducing here turbulence or generating turbulence, and you see the difference in the pressure here. And that actually leads to some insights into the wave growth mechanism, which are still not completely understood, how the waves of the ocean actually are generated. And this is, of course, the most important driving of the ocean, the surface waves. And we hope that we can contribute with these measurements to better ocean forcing functions then at the end. There are also observations of large-scale ocean and atmosphere, which I cannot cover here. But we also stretch to the other end, to the mathematics. And this is an example from our postdoc Florian Nöthen. He worked on covariant Lyapunov vectors, which can describe instabilities, flow instabilities, in a better way than our traditional methods. You can have some general background flow, and they are corresponding to the natural modes related to Lyapunov exponents. That was also applied to realistic models of the atmosphere. And in the second phase, we hope that we can explore these methods. And of course, there's a lot to be said about our second phase, which I cannot cover here, because time is restricted, of course. So we have this project, and first phase was concluded, and then we applied for second phase. Then Corona came, then it was a little bit of an intermediate phase. But then this proposal was granted, and we have now the second phase for another 4 years. And then after the second phase, we also hope to get a third phase for another 4 years of this project. And you have some impression where we are working on, and of course we will continue this line of research also in the next couple of years. You can find more information here on our website, and you can check YouTube and Twitter channels. There's active social media participation by this project. You might want to check that. Here's a photo of our group, and from last year or from the year before, where we had a retreat in person. And in the second phase, we actually have also Mercator Fellows. The DFG are electing Mercator Fellows for special projects like ours, or for large projects like ours. And we decided, and we asked Laura Zonner, David Marshall, Jacques Van Nest, and Kevin Lamb to contribute. And they agreed, and they are also here, and they will give talks in this workshop. And they all do, of course, work related to our work, and we hope that we can collaborate and learn from each other. And I hope that you know now what Mercator Fellows are about, and they will also give talks here. And with that, I want to skip here the details about our projects, and without further ado, we can just start here with the first talk, I think, by Jacques Van Nest, which is one of the Mercator Fellows. So, and that's the plan here for today. First session, second session, third session, with breaks in between, right? And as Monita said, during the breaks, but also during the discussion session and later, of course, you can always go to the GatherTown site to meet in person, actually. That's a disadvantage of this workshop, of course, to meet. We cannot meet in person, and we cannot chat, and we cannot have dinner and everything, but we can go to GatherTown and talk to each other. Not in the large group, but individual groups can form there, and you can talk to each other. So go there and try it out, it's fun. Okay, then Jacques, do you want to start?
Just before, because I'm chairing the session, so sorry, just two brief things regarding some technical details. Please, everyone who is actually in the Zoom meeting, use your full name as your meeting name, so that we can double check with the registered list. And if you have questions, please put them in the chat as an exclamation mark, or write them in the chat, and then we will forward them at the end of the talk. And then I think with that, Jacques, should I give you like a 3-minute warning at the end? So you have 20 minutes, and then I give you. Is that fine?
Yeah, because I don't see my timer actually. So.
Then I'll let you.
Can you see my?
Then I'll let you know 3 minutes. Yeah.
Okay. Can you see my slide properly?
Yeah.
Yes.
Okay, very good. Okay, well, thank you very much for the invitation and for organizing this meeting. I think it's my first kind of full-blown online meeting. It's going to be interesting. We'll see how GatherTown is performing to replicate interactions between people. All right, so this talk is about how inertial gravity waves are being scattered by geostrophic turbulence, and it's joint work with Hossein Kafiabad, who's around, I think, and my former PhD student, Miles Savan. So what is the question? Well, as all of you know, in the atmosphere and the ocean, there's this mixture of balanced motion, typically in geostrophic balanced motion, and inertial gravity waves. And so very often you can assume that the velocity of the flow is much larger than the velocity of the gravity wave, so they are fairly small amplitude objects. The flow can be taken to be in a quasi-geostrophic balance, a reasonable assumption, so because the velocity of the flow is also quite small compared to the Coriolis frequency, and this flow is largely turbulent. Okay, so what we wanted to do is to develop some kind of theory for the generic behavior of inertial gravity waves once they are kind of plunged into a soup of quasi-geostrophic turbulence. Okay, and a theory like that has to be statistical in some sense. So immediately I'm going to tell you what the assumptions are so we know where we stand. So the first thing we're going to assume is that the waves are linear. So in this business there are a lot of theories about wave-wave interactions. There will be nothing of the sort in my talk. The second assumption is that the waves are going to have scales which can be of the same size as the scales of the flow. Okay, so this is somewhat unusual assumption in that very often waves are treated by something like WKB, where you assume that the wave scales are much smaller than the flow scales. Here we're going to deal with similar scales. But I'm going to be in a regime where the flow is weak. And the way this is characterized is by the fact that the Doppler shift is a small contribution to the frequency of the wave. So the intrinsic frequency dominates. In other words, the waves are essentially waves in a resting basic state, which are slowly or gently modulated by the flow. Incidentally, if someone could switch on the camera, it would help me a bit not to talk completely in the vacuum. Thank you. And finally, I'm going to assume that my flow is QG, so defined by a stream function. And the stream function will have some given statistics. Oops. Okay, so a motivation for this work is what is happening in the atmosphere and the ocean in ranges of scales which are sort of smaller than the scales of, say, Bartlett eddy. So these are called the mesoscales in the atmosphere and the sub-mesoscales in the ocean for historical reasons. And what is happening there is that the energy spectrum is fairly shallow and as yet unexplained largely. Okay, so in the atmosphere, this is known since the work by Nastrom and Gage in the mid-80s. And here is what they found, sort of replicated from more recent data looked at by Callies et al. So if you fly an aircraft through the atmosphere, the upper troposphere probably, and you take a Fourier transform of the velocity field that you observe, you can cook up a kinetic energy spectrum as a function of wave number, inverse scale. Okay, and the typical behavior is that at very large scales you have a very steep spectrum, k to the minus 3, which is well explained by balanced motion, by a quasi-geostrophic turbulence. But then, so this is the black curve, the total energy. Then the spectrum shallows to something which has been identified as a minus 5/3 power law, but can also be described as by minus 2 power law, depending on which data set you look at. Okay, so this spectrum is still sort of mysterious. Reasons for its existence are unclear. Callies et al. Managed to do something interesting, which is that they took the full energy spectrum, so this black curve, and split it into two contributions. So one is the balance contribution, QG contribution, which is the red curve, which explains totally the energy at the larger scales. The other contribution is the blue curve. This is the inertial gravity waves. Okay, so they assume that you can split the total flow into QG plus inertial gravity waves, and then you see that at mesoscales here, so from 500 kilometers down, the shallow part of the spectrum is attributable to those inertial gravity waves. And in the ocean, you can do the same thing. You sail a ship rather than fly a plane. You also make measurements of velocities to create this energy spectrum as a function of scale. And depending on where you are, you find pictures of this type where you have the total energy is in purple here. So there's some energy here which is probably some form of vertical flow. And then at smaller scales, in the sub-mesoscales, you get a fairly shallow spectrum, k to the minus 2 again, which seems to be attributable to inertial gravity waves. Okay, so this is a somewhat controversial interpretation. I think it's fair to say that this data analysis tells you that the observations are consistent with linear inertial gravity waves. Linear here means that they behave to leading order like waves in a medium at rest. But the observations don't tell you, for instance, why you would have this k to the minus 2. Okay, so what we wanted to see is whether we can explain this k to the minus 2 by thinking that those waves are actually modulated and refracted by the presence of the quasi-geostrophic flow, so the large-scale flow. Okay, so one thing to remember, of course, is that when you look at a spectrum like this is a logarithmic coordinate, so there is much more energy in the balance flow than there is in those gravity waves. Okay, so it makes sense to think of the balance flow as being fixed, and then the gravity waves as traveling in that background. Right. So just to visualize a bit what we are talking about here, here is a simulation that Hossein carried out. So this is a simulation in which you start with a QG flow in a triply periodic domain, and you add some inertial gravity waves. I should maybe start at the beginning here. There we go. So on the left here, you have a horizontal slice showing you a vorticity field. So this is typical QG turbulence with vortices which gently merge. This is a decaying situation. And then we add a plane wave, and we see this wave because we are looking at the vertical velocity. So the balance flow, the QG flow, has not much of a footprint on the vertical velocity. So mostly you see the wave, and then you just let this evolve. And what you see is that the vortices do what they do, so they kind of rotate around and merge. And on the other side, the gravity waves get scattered very quickly, so you started with a definite plane wave with a certain clear, well-defined wave number. Quickly the scales are shortened, and also the flow becomes pretty much isotropic. So if you were to look at this as a random field, you'd characterize it by being homogeneous and isotropic, no preferred direction. And also, if you looked at the typical scale, it has been reduced considerably from what we had at the beginning. Right? So if we play again, you see that the scales shrink very rapidly as the waves getting more and more isotropic. So this is the kind of process that we want to describe. And of course, we're going to do this in a statistical sense. Okay, so what we have done is to derive two models, if you like. One is a subset of the other one. And those models are characterized by a kinetic equation describing the evolution of this wave field, or the wave amplitude, and then a diffusion equation, which is a limiting case of this kinetic equation. So the hypothesis here, so what we do, I'm not going to go into the kind of gruesome details of the derivation, but we start with the linearized boostiness equation, so linearized about the QG field. It's a QG field, so we can assume that it has a small Rossby number. In particular, what it means is that that field evolves on a time scale which is much lower than the wave time scale. And this flow we just take to have some given statistics. Okay, so we don't pretend that we understand QG turbulence. We just take from standard theory or from observations what are the statistics of this flow. And in fact, the only statistic we're going to need is the correlation function, so the energy spectrum. Then, as I mentioned at the beginning, we make no spatial scale separation assumption, at least initially, so the wave scales are the same as the flow scales, but we nonetheless allow some spatial modulation of the wave amplitude at much larger scales than the wave scales themselves. Okay, so what we're describing here is some superposition of wave packets, if you like, which are modulated over long scales. Now, the key quantity to describe this kind of field is what I call here the phase space energy density. Okay, I call it A, which is the energy density at location X and wave number K, okay, wave vector K. So defining this object is not completely trivial, because you somehow have to do both a Fourier transform, but also keep some spatial information in this business. Okay, so this is done following sort of standard theory of waves in random media, using a Wigner function to define uniquely what you mean by this phase space energy density. So just to explain, I mean, if you use a W-Kibbe approximation, then this object is defined very naturally, because all the scales except for the wave scales are much larger than the wave scales. In our case here, that's not true, right? The flow scales are similar, so we need to be a bit careful in the way we define this energy density. And so what we can show is that without any spatial scale assumption, this phase energy density obeys a kinetic equation. I'll show in a second what it looks like. And this kinetic equation can be simplified if you assume that the wave scales are much smaller than the flow scales, so the wave numbers are much larger than the flow wave numbers. That's the WKB limit. It simplifies into a diffusion equation. Okay, so just to kind of summarize what regimes we're talking about here. So what I'm showing here is the wave number of the wave, and there are two kind of key wave numbers to keep track of. One is a typical wave number of the flow, so that's the flow scale, and then much smaller than that, because of my small Rossby assumption, is this scale here, frequency of the wave divided by the typical velocity of the flow. That's the scale at which the Doppler shift becomes makes a significant contribution to the frequency of the wave. Okay, so this is the place where the flow starts to be strong in some sense. So WKB, the traditional WKB approximation, will work as long as the wave scales are much smaller than the flow scale, so the wave number of the wave is much larger, so in this range here. What I'm going to talk about is limited to this regime of weak interaction where the Doppler shift is negligible, or not negligible, but weak. Okay, so I'm going to describe this entire regime from any scale you like at the large scales for the waves, all the way to this strong interaction limit. And then, in general, I have a kinetic equation describing the whole range, and then a kind of sub-range is described by this diffusion equation. So let me show you what this looks like. So here is a kinetic equation that you obtain, which looks like all kinetic equations, really. On the left, we have transport by the group velocity, so that's a kind of familiar term, right? We have refraction by the variations of the properties of the flows over the large scale. And then on the right is a scattering term, which comes from which represents the energy exchanges between gravity waves, which are caused by the presence of the flow. Okay, so there's this quantity here, sigma, is a cross-section. It tells you the rate at which energy is exchanged between gravity waves with wave numbers k prime to gravity waves with wave number k. Okay, so once you compute this little sigma, the big sigma is just its integral over k prime, and you know everything about the scattering of gravity waves, so you know everything about the way the turbulent flow is redistributing energy in the wave field. Okay, so what is key is that this scattering cross-section is not any function. It has lots of complicated terms, but the most important thing is that it has this Dirac term here, or factor, which tells you that energy is going to be redistributed between waves with the same frequency. Okay, and also the way the flow comes in this cross-section is through the kinetic energy spectrum of the flow. Okay, so the only property of the flow that you need to know is the kinetic energy spectrum. So why do we have this constraint of redistributing energy on among waves of the same frequency? Well, that's simply because we've assumed that the flow varies slowly, so effectively compared to the waves it has a zero frequency. We also have assumed small amplitude for the flow, so the only exchanges that we're going to get are going to be through resonant triad interactions. And the triads that are described here are triads involving two wave modes, okay, one here, which interact with the mediation of a flow mode, a vortical mode. Okay, and the relationship to be resonant between the frequencies is that the frequency of the wave mode plus the frequency of the flow, which is here in fx0, has to be the frequency of the second wave mode, which is again the same omega. Okay, so when the flow is weak, it evolves slowly, hence the frequency of the gravity wave stays put. There's only one value. And this kind of interaction involving two wave modes and a flow mode have been termed catalytic interactions because we didn't do that, but if you look at the effect that this interaction has on the flow, you'll find that it has no effect. And that's because essentially, the gravity waves don't have any potential vorticity to play with, and so they cannot influence the flow, which is entirely controlled by potential vorticity. So the moral of the story is that all the energy exchanges I'm going to be describing are going to be on a constant energy surface, And as you know, for inertial gravity waves, the constant energy surface in Fourier space, in wave vector space, is a cone. Okay, so we expect energy to be redistributed on a cone in wave vector space and never leave this cone. Oops. I have a technical problem here. Right. Are you still with me?
Yeah.
Okay, I don't know what's happening. I'm going to reopen it with preview, perhaps. Right, so this is the image I wanted to show you. So this is these are snapshots from the simulation I showed you previously. And what I'm showing here is the Fourier analysis of this field, where the axes are not shown here, but are the three components of the wave vector. We start in simulation with a plane wave. So a plane wave has a single wave number, a single wave vector. So all the energy sits at this green dot. And then as the flow evolves, you see this energy being redistributed in Fourier space, in wave vector space, redistributed mainly along the cone corresponding to constant frequency. Okay, so you see, I mean, it's interesting what is happening. You first have a kind of isotopization, so the energy gets redistributed along circles, and then it also gets to smaller and smaller scales, so it kind of escapes to infinity along the cone. And also notice that, so this cone here has two naps, as they're called, so two half cones, if you like. One corresponds to waves propagating upward, the other one to waves propagating downwards, and you see that there is some exchange. So waves going up, actually it's a leak energy because of the presence of the flow, to waves going down. So this is what is being described by the scattering equation.
You have 3 minutes left.
Oh, already, Jesus, not very good. Okay, so right, so I'll skip this to tell you that when the wave scale is much smaller than the flow scale, then the scattering equation can be simplified into just a diffusion equation. So you get this diffusion in frequency space, or in wave number space rather, which is the limit of the complicated scattering term that I had. Okay, and the fact that energy is only redistributed along the constant frequency cone is marked by the fact that this diffusivity tensor is perpendicular, if you like, to the group velocity. Okay, so that's the manifestation of this phenomenon. Okay, so what I want to show you is, so I didn't give you the details, but we worked out what the cross-section was. We worked out what the diffusivity tensor was. And so we have those predictions for how energy is going to be redistributed along a cone, and we tested that against direct simulations, okay, using a pseudospectral code with some values for the parameters. The setup is more or less the one of the simulation I showed you, except for the fact that we start with an initial condition which is isotropic. So the only thing we keep track of really here is propagation along the cone, not in the azimuthal direction of the cone, okay? And so here are the kind of results that we get. So those figures are a bit maybe difficult to make sense of. This axis here, the k-axis, is the coordinate along the cone, and it has both positive and negative values corresponding to the upper and the lower nap of the cone. And then time is along this way, and this is the energy. Okay, so what we see, so we start with some spectrum here, okay, with the black curve. And then what we're following is the evolution in time of this spectrum, comparing the black curve, which is a numerical simulation, with the red curve, which is the full scattering theory, and the blue curve, which is the diffusion approximation. In those two panels, so these are two different frequencies for the waves. We start with a wave which has a scale shorter than the flow scale. So this is the peak wave number for the flow. And you see that both theories kind of overlap, and they predict the spectrum pretty well. Oops. What you should see also is that in the diffusion approximation, there's actually no exchange between the two naps of the cone. That's completely ignored. Okay, that's something which is captured by the full scattering theory. And then this is when we take the wave scale to be similar to the flow scale. I mean, it's probably a bit quick for you to get everything, but what is happening is that the full theory gives us a good prediction of the evolution of the spectrum, whereas the diffusion approximation is rather poor, as expected, because we're not in the regime where it's supposed to hold. Okay, so just the last point I want to make, which is the most important one, is that so what I've shown so far were initial value problems. We just drop some inertial gravity wave energy at some wave number and watch it evolve. You can also think about a force problem where you have a continuous source of gravity waves. In that case, if you assume isotropy, you can also get rid of the angular direction, and you end up with a diffusion equation. So this is in the diffusion approximation when the wave has a scale smaller than the flow. You have this one-dimensional diffusion equation, diffusion in k-space, and you can look for stationary solutions, and they pop out completely naturally. There are two possible stationary solutions. One is a k to the 2 power law, and the other one is a k to the -2 power law. So this one is obviously going to be for small scale, for large scale waves, small k. This one for large k, small scales. Okay, so we find that completely naturally, because the diffusivity depends in an interesting way on the wave number here, okay, this k to the 5 dependence, very naturally, if you let waves evolve in a turbulent QG flow, the energy distribution is going to settle to k to the -2 spectrum on this cone. That corresponds to constant energy flux. Okay, so that's interesting because it's completely consistent with the observations of the spectrum, the shallow part of the spectrum, in both the atmosphere and the ocean, which is something like a k to the -5/3 or k to the -2. At the level of accuracy of the observations, -5/3 and -2 are almost the same thing. And so we believe this is a strong argument to this interpretation of the shallow part of the spectrum being due to inertial gravity waves, okay? Because not only is it consistent in the sense of the dispersion relation and also the polarization relation, which is what Callies et al. Showed, but also is what we can explain is why, if you put a bunch of gravity waves in a turbulent flow, you get precisely this power law spectrum. Okay, so that leads me to my conclusions. So what I've discussed briefly is a complete statistical theory of linear gravity waves in a turbulent flow, which is assumed to be weak. Okay, so what we have are those energy exchanges which are between gravity waves of the same frequency, which are mediated by the turbulent flow. We have this diffusion approximation, which is valid when the flow scale, when the wave scales are much smaller than the flow scales. Okay, it's kind of nice because it's very easy to understand intuitively what the diffusion is. The full scattering term is a bit more complicated, but roughly speaking, it plays the same role, right? So it redistributes the energy in a kind of smoothing way, taking energy from the regions of high amplitudes to regions of low amplitudes. So the diffusion approximation has this very nice feature of having this equilibrium k to the -2, which is consistent with observations. The diffusion approximation has this weakness that it doesn't describe any exchange between the two naps of the cone, so between upward and downward propagating waves. Now, there are a few things we haven't really discussed. I mean, one is that I've completely focused on a scenario where the waves were already isotropic. In fact, there's an interesting phase in which, as I've shown in the initial movie, if you start with a plane wave, very quickly the turbulent flow leads to this isotropization. It'd be interesting to study how that takes place, what is the time scale for this. The other thing we haven't discussed but can also be done is I've already shown results for homogeneous situations where the waves were completely homogeneous in space. You can, because we have this spatial dependence of our equation, discuss scenarios where you have a plane wave at a given location, which then moves away from that location. So this is something which we did about tides, using a very similar description where you have, so these are two horizontal coordinates. We see a surface elevation field. There is a wave maker here, and so the wave maker generates a plane wave, which propagates over turbulent flow. And you see how in space now this turbulent field gets more and more isotropic. Okay, so, and finally, I mean, one thing which probably will crop up later on during the meeting is that in our approximation of slow flow, the frequency of the waves stays put. Okay, so we can relax that and start worrying about the effect of the slow change of the flow and how it leads to a very weak diffusion of wave energy across the constant frequency cone. Okay, that's my talk, and apologies for overrunning quite a bit.
Okay, thanks, Jack. I think we should keep going, but maybe one quick question. I'm not sure if the question by Boris is already sorted, and then is that already clarified in the chat? Boris? Maybe then, sorry, I see two.
I didn't see that it was clarified. I didn't see the answer to it.
There was a remark in the chat that was answering to that question, but maybe ask the question then.
Well, probably kind of, well, okay. The question was why Jack didn't consider inertial waves in addition to internal gravity waves, because inertial waves may be even more important than gravity waves.
So these are inertial gravity waves, right? So I have the full range of frequency. So the theory works as well for inertial waves as it does for any gravity wave.
I see. I didn't see dispersion relations.
Yeah, no, I didn't show. That's right. So these are full inertial gravity waves. Yeah.
Okay. All right.
Okay. I'm sorry. There's several more questions, and I see some hands there. I think we have to skip this for now. We will have time in the break later for these questions if we have time for that. Let's just keep going for the moment with the next talk.
Okay.
Then Jeffrey can maybe jump in now.
All right. Hi. Am I live here?
Yes, we can hear you.
Okay, great. Well, good morning. This is thanks for inviting me. This is decidedly the earliest talk I've ever given. You should see the sun rising behind me here in a little bit. Let's see, let me share my screen. Okay. All right, so this is a wave vortex decomposition for rotating Boussinesq flows applied to arbitrary stratification. This is work I did with Pascal Lalong, and who is with me at Northwest Research Associates in Washington, and Miles Sundermeyer, who's at University of Massachusetts, Dartmouth. And thanks for Manita for inviting us here. This is fantastic. Really excited about all the talks here. So I'll jump right into this. So let me set up sort of our interest in the problem we have here. So in the left panel, I have a buoyancy frequency of a stratification profile from the Sargasso Sea in the summer. So what's notable here is that this is on a log scale in both depth and buoyancy frequency. So you have a seasonal picnic line here that is several orders of magnitude higher in buoyancy frequency than the buoyancy frequency at depth. You can see the thermocline further down at depth. And this problem was interesting to us because there were a series of lateral dispersion experiments that were performed in this stratification profile over the span of a few days at around 30 to 40 meters, so below this picnic line. And the various hypotheses for this were based around stirring from internal waves or vortical mode dispersion. And so one of the things one wants to ask immediately is, well, what part of the flow here is from internal waves and what part's from vortical motions? So the basic theory for separating out these types of motions at any given moment in time has been developed for triply periodic domains with constant stratification. But this is decidedly not constant. And in fact, what I've done here, I've shown two different internal wave mode solutions. So the vertical dashed line is for a wave that's fairly hydrostatic, and that's this center plot. You can see the 10th mode for a nearly hydrostatic wave and what that looks like. So again, noting the log scale with depth, this has 10 crossings of 0, and you can see it has highly variable wavelength depending on the depth you're at. Now, if you look at the dotted line, a wave now more confined to the pycnocline region. Again, this is sort of a classic wave solution here. There's also 10th mode, so it has 10 zero crossings, but it has no variance below about 100 meters or so, right? So the key features in this stratification are, well, clearly variable stratification matters a lot, and so applying constant stratification theory wouldn't be appropriate. And also that non-hydrostatic motions are really important. These interesting waves that are trapped near the pycnocline matter. So what I wanted to talk about was basically show how we extended the basic theory here. Wow, I am really dark. I'm sorry about this. I should turn on the light. We're adding significantly more realism by including the variable stratification and vertical boundaries. So one of the surprising results that comes from this that I'll talk about briefly is that actually modeling in a wave vortex space is actually more numerically efficient than traditional spectral methods. And there's a number of interesting diagnostic techniques that come out of this, including some new ways of assessing nonlinearity, and also the ability to, this has been done before in other contexts, but we show how you can isolate different transfer mechanisms between wave and vortex modes. So this came out of a series of a couple papers, most recently their JFM paper, and a paper that's published in James a year ago with Schaefer-Smith. So what is the idea in an abstract sense? So the basic idea is that you can take your physical variables or your equations of motion and you project them onto the linear and vortex solutions. So for example, this was done by Peter Bartello in 1995 with constant stratification in non-hydrostatic waves. And so this is basically, you can think of this as just another spectral basis. And what's cool about it, right, is that you take your 5 variables or 5 equations and you can reduce them to 3 without any loss of information. So in particular, that's you take U, V, W, rho, and pressure, and you project those onto amplitudes of your wave and vortex mode. So I use A plus and minus for the positive and negative waves and A0 for a vortex amplitude. This is nicely described as an orthogonal divergence-free basis in Gerardo Hernandez's paper and Leslie Smith. So, but it's more than just a complete basis, right? So there's lots of complete bases which you can apply a lot of spectral methods. What helped shape my understanding on this was a paper by Schaefer-Smith and Jacques Vanest in 2012, was that the way of thinking about this is that a good or useful basis also diagonalizes energy. And the idea here, right, is that you can add up the energies from each of your solutions. You take your components, simply add them together to get the total energy, which doesn't work, of course, in general. And this is physically meaningful because then you can actually give some sort of sense of identity to a wave, right? So, you know, a wave of a particular vertical structure with a particular frequency is a unique object in your space, separate from some other one that you observe at some other time or same place. So the basic idea proceeds as follows. This is the, I'm showing here the linearized equations of motion. And we have a number of assumptions still. This is non-hydrostatic, so you have dw dt still in here. This is F-plane, rigid lid. There's no surface buoyancy anomaly. It's doubly periodic, but importantly, we're allowing for variable stratification. And so n squared of z is just ddz of the background mean stratification. I also I use eta to represent your buoyancy anomaly or your mean density anomaly, which is a scaled version divided by the mean density background. And this is sort of the more useful object here because that's what needs to be projected instead of the density itself. This system, the QG potential vorticity has no time fluctuation, but Ertel potential vorticity does. And so this is sort of the more relevant quantity in this case. This is QGPV and not Ertel PV for the linearized equations. And this is just as in Wagner and Young in 2015. Okay, so the key thing that holds this all together is the vertical eigenvalue problem. So I'll go back here for a sec. So if you do this classic separation of variables that you see in the textbooks, and there's only two of these equations have anything to say about the vertical structure, and that's the vertical momentum equation and the continuity equation. And so that gives you constraints on your vertical structure functions. So what I have here is n squared minus omega squared, where that omega squared comes from the non-hydrostaticness. This is all from the vertical momentum equation. And then F equals h dg dz is from the continuity equation. And those together can form an eigenvalue problem. So this is typically written as a function of omega squared. Now, don't forget to n squared is a function of z here. But when you want to apply this method at any instant in time, then constant frequency is not the relevant quantity here, but in fact, you need to convert that to a wave number. So this is where the dispersion, use the dispersion relation. And we discussed this a little bit in the paper with Schaefer. So here you get an eigenvalue problem. Now that depends on your wave number and results in a series of modes that diagonalize energy. This is important here. And this is your orthogonality condition. All right, so when you want to apply this to the equations of motion, here's a nice, I think, kind of a nice way of sort of organizing the solutions that come from this, organized by wave number and mode. So you take your U and V and your density, and you take a discrete Fourier transform and then project it onto the vertical modes. And you can, in this table down here, I have it sorted by wave number K and vertical mode number J. And all of the different solution types can be organized in little boxes in there. So your internal gravity wave solutions are for K and J greater than 0 in U and V and in density anomaly. You get your geostrophic solutions appear in those same cells. Inertial oscillation solutions correctly limit, just as in Jacques' case, as K goes to 0, and are only in U and V. The mean density anomaly shows up as the limit on the geostrophic solutions as K goes to 0, for only in the density anomaly part. And then there's a barotropic geostrophic solution, which does not come from any of the limiting cases, that shows up in U and V. So really, you could argue there's sort of 3 separate solutions outside of those limiting cases. All right, so let's see.
You have about 3 minutes left.
Oh my gosh, wow. Okay, so the basic idea here is this is just a linear transformation. So you can take U, V, and eta, and you just apply a transformation that I've written here as S inverse and T omega inverse, and you get your wave and vortex coefficients. You apply that at any instant in time with your entire fluid flow. And the basic thing is, I'm showing it here for hydrostatic case, but do a Fourier transformation, do a vertical projection, and unscramble the amplitudes. This T inverse is a time winding, well, in this case, unwinding operator that unwinds the phases of your internal waves back to some initial time. And you perform that operation on any of your variables, and voila, all of the coefficients, A plus and A minus, now get sorted into into their own little bins. So you can literally, like in the code in MATLAB, this is literally how this shows up. And then now you can simply square and sum these and you get the amplitude of your flow or amplitude of any of the constituent parts. Apply this at any instant in time. So I like, so I'll cruise through this then, I guess. So there's some cool diagnostics you can do with this. This becomes an alternative way of sort of defining what a linear wave is. So it's not alternative, but the linear equations of motion, when you project them in this basis, are simply the ddt of the wave amplitudes don't change in time, which means if you examine a flow over a time series, you can go look for changes in those amplitudes and see how much those amplitudes change, and therefore assess. That gives you another measure of nonlinearity, which doesn't always connect with linearity. You can crank the amplitude of a flow incredibly high, 10 GM, and you'll find that your waves are still stirring very linearly often. You can also, of course, project the nonlinear equations of motion themselves straight onto this basis and identify energy transfer mechanisms. So this is an example that also Jacques mentioned. This is one of the terms for the advection of your geostrophic vorticity by inertial oscillations that transfers energy from the inertial oscillations into your internal gravity wave field. So the final thing I want to hit on is the modeling implications for this, which I think are pretty cool. So one of the things we sort of unexpected from this was that there was a model run where we had 256 grid points in the vertical, evenly spaced, and it only resolved 19 vertical modes. And what's interesting about this is that this is from the non-hydrostatic, spectral model. And what's interesting is that you don't really realize it, but a lot of physics is being stopped. You can't cascade to higher wave modes here, and you don't really see that unless you go and look to see which wave modes are resolved. So now it's interesting that in the constant stratification case, the projection onto the wave vortex basis provides an equivalent representation to the usual pseudospectral methods with the same numerical complexity. So there's sort of no reason not to run your code in this situation. As soon as you have variable stratification, you actually can start to gain in efficiency. And that's because your grid points are spaced at the Gauss quadrature points for your vertical modes. And so finally, then what I'll say is that your equations of motion projected in this basis have a number of cool reduced models that can come from this. So you can, of course, shut off transfers with the QG, with the geostrophic modes, and you get a wave-only turbulence model, again, with variable stratification. You can shut off all the waves, and you get a stratified QG model. You can limit yourself to a single mode, and you reproduce shallow water. And similarly, of course, QG is also embedded in here. So this code has been available actually for a couple of years on GL OceanKit, although I've recently rewritten a lot of this, and you'll see it moving to another repository in there within that repository. And so I think I'm out of time. So I'll just say that the highlight here is that we've extended this wave vortex decomposition, which I think has been used quite a bit, to be significantly more realistic. And I think there's a lot of really cool applications that we can do with this that I'm excited to show and to play with. So.
Okay, thank you, Jeffrey. We have time for one quick question, I guess. Marcel, I think, raised his hand. So that's the one I see at least. So maybe Marcel can ask.
Okay, so there is the formulation of the Boussinesq equations in terms of potential vorticity. So in this case, the Ertel potential vorticity, and then divergence and ageostrophic vorticity variables, which is, for example, advocated by David Dritchell quite a bit. And I believe David also has working codes that make use of that decomposition, which seems to be different but philosophical similar to what you are doing. Could you comment on that?
Oh, I haven't actually dug into that. I don't know. That sounds really interesting. Yeah, I don't have, unfortunately, don't have a lot to say about that.
But he sort of has the same list of things he wants to do. He can also, at least I guess, to leading order in whatever ROSPI or so, it should be the same thing as you are doing. But of course, the technical details are quite different from the two approaches. But I think from the point of view, what you're getting out of it, I think there might be a lot of overlap.
That does make sense. I mean, yeah, these are, you know, the linear solutions, it might be the starting point for a whole bunch of, you know, perturbation expansions. And so I would expect it to show up in a couple different contexts. That's, yeah, I will look into that. Thank you.
Okay, thanks. I think we have to move on, but by the way, please use the chat and use the opportunity in the break if you want to talk to the presenters, because that's a good thing with online things. You can still chat to them during the whole meeting without having to put up your hand. So, and I think there's a few questions to Jack as well that he said he will answer maybe in the break. So then we move on to Spencer Jones. Yeah, you can start. We can see a screen, so that's working.
Great. Okay, so I think, yeah, the first thing I should say is, unlike the previous two talks, this is very preliminary work, and what I'm looking for here is more, I'm going to present what we're trying to do, and I'm hoping that we can get some feedback from experts who are here. So yeah, it would be great to talk about this problem either after the talk, in gather.town later, or, you know, offline. Feel free to reach out to me offline. So yeah, this is work that I'm doing with Ryan Abernathy and Schaefer Smith. Ryan and I are at Columbia, and Schaefer is at NYU. And we're looking at how we could maybe use Lagrangian filtering for flow decomposition in ECHO LLC 4320, which is this really high resolution global version of the MIT GCM. Okay, and so the motivation for this work is really that the SWAT satellite is going to go up in the next year or so, and that will provide really quite high resolution altimetry measurements down to scales of about 15 kilometers. And so those observations are going to contain valuable information about the velocity field near the surface of the ocean. And so our kind of large scale goal in this project is to see whether we can find information about the velocity field that's relevant for studying ocean transport from the sea surface height. And so I guess this is another difference with the previous two talks, is we're really interested in the waves because we'd quite like to remove them from the signal. As I talk about on this slide, we want to explore the relationship between sea surface height and the transport relevant flow. You know, geostrophy works pretty well for sort of low resolution altimetry and models, but at these kind of small scales, we need to think in more detail about other terms in the balanced velocity other than just the geostrophic balance, and also waves. And like I said, we're kind of interested in removing the waves because there's a stronger relationship between the balanced flow and the sea surface height than there is between the total flow and the sea surface height. And waves are really creating noise on top of that. And so this is just an illustration of kind of the setup and this concept that the sea surface height perhaps it is more related to the balanced flow. So this is the Agulhas region. This is Africa right here. And so you can see that there's kind of quite a smooth sea surface height, but also on top of it, there are tides. This model has a whole, all of the, or a lot of the wave flow that is in the real ocean. And then this is the horizontal kinetic energy. So you're going to see in this movie, yeah, there are, you can see the wave flow as well on top. the balanced flow. So so yeah, this is a model that we're going to use to sort of explore this problem a bit. Okay, hang on. There we go. So people have started to think about this already. This is a figure from Torres et al. 2018. It's a figure showing wave number frequency space in the same model, but in a different region from what we're looking at in the Kuroshio region. And so what they plotted is, so this is frequency, this is wave number, and you can see that there's this kind of whole range of scales and frequencies that are found in this model in the surface velocities. And this figure, which I like very much, sort of breaks down the different kinds of velocities that there are. So in the low wave number, low frequency region, you get Rossby waves. And then as you go to higher frequencies and wave numbers, you have the mesoscale balanced motion. And then you have sub-mesoscale balanced motion. And then as you get to frequencies that are higher than the Coriolis frequency, you get unbalanced sub-mesoscale motions. And you also get these internal gravity waves. So yeah, these green lines are the baroclinic modes. And so this is where the internal gravity waves are. And so, yeah, so in general, balanced flows tend to have these lower frequencies, frequencies lower than F, and the wave flows tend to have frequencies higher than F. And yeah, the internal gravity waves tend to be over here at the low wave numbers, and the non-wave, like unbalanced flows, tend to be over here at the higher wave numbers. But so, okay, so we are trying to separate this unbalanced flow from the balanced flow. So perhaps we could just filter everything higher than F. But as Jacques mentioned, there's this problem of Doppler shift, which is internal gravity waves have frequencies higher than F in coordinates following the flow. But because we have a flow at a whole range of scales, we actually aren't able to, if we just filter in Eulerian space, we're going to have Doppler shifting of those frequencies, and they're going to contaminate the flow that we have left over. So for example, if there's a velocity of 0.05 meters per second, and the horizontal wave number is 2 pi over 2000 per meter. So, I mean, you know, these are sort of typical values maybe. Then you might have an error in if you're looking at the frequencies in Eulerian coordinates, you might have an error of 1.25 F, and that can be in either direction. So, for example, you might find your internal gravity waves at frequencies that are lower than F because they've been Doppler shifted. Now, Shakespeare and Hogg 2017 came up with this method to tackle this by filtering in Lagrangian space. Now, what do I mean by that? So the method I talked about before, I'm going to call that Eulerian filtering. It's just kind of standard frequency filtering, where at every point you take a velocity time series and at that point, and then you are going to put a low pass filter on that time series at every individual XYZ point. Whereas if you are doing Lagrangian filtering, you have to do several more steps. You advect some particles in the horizontal flow field. You record velocities at regular intervals along the particle trajectory. And then you take, for each particle trajectory, you're going to do the low pass filter. So you're applying the low pass filter along the particle trajectory. And then you interpolate your velocities, your filtered velocities, back onto a regular grid. And so Shakespeare and Hogg did that. This is their frequency spectrum, and they did this by they just basically filter out everything, all frequencies higher than 0.9 F, but they do it in this Lagrangian way. It's kind of slightly easier for them because F is constant throughout their domain. But they seem to quite successfully remove the wave part, or separate the wave part from the non-wave part. So this is a visualization of their total flow. This is the non-wave part, and then this is the wave part. And so, yeah, you can see that they successfully, even though they're doing a method that is filtering based on frequency, you can see in the wave number space that they're sort of separating waves. And so we decided to apply this in LLC 4320. And so we're doing the same set of steps. We seed the model with a grid of particles, and we actually want the particles, the interpolation steps to be easy. So we seed the particles on a regular grid, and then we run the particles both forwards and backwards so that the middle of the trajectory will be on a regular grid. And so we do that, and then we apply a convolution filter to filter out these high frequency motions. This is just sort of like a visualization of what that convolution filter is actually doing. It's just smoothing out the high frequency motions. And then in spectral space, what that looks like is this. So the black line is the Coriolis frequency in the middle of our domain. The blue line is the spectrum for the full velocity field. And then the orange line is our filtered velocity field. So we're sort of filtering out most of the energy up here at frequencies higher than F in the middle of our domain. And then, yeah, we interpolate the filtered velocities back to Eulerian space, which is really made easy by the fact that we started with a regular grid of particles. So this is the point where I'm starting to want some feedback from people. So we have some preliminary results. This is the sort of filtered horizontal kinetic energy. So that's the non-wave part. And then this is the wave part. And so, I mean, when you look at the wave part, you can see, it seems clear, it contains internal gravity waves. But how do we know that we did this very well? It's really not clear to us how to figure out whether we have successfully separated the two portions of the flow. And so I think we're looking for suggestions from the audience about how to do that. So I'm just going to tell you a couple of things that we've tried, but this is kind of the main question that I have if anyone has suggestions. So we're currently exploring two ways of comparing Lagrangian filtering to sort of Eulerian filtering and other methods. One is we're plotting the filtered flow in wave number frequency space, and that's what I'm going to show next. And then we've had a look a little bit at the momentum budget as well, because presumably we can see is the flow balanced by looking at the momentum budget. So look, okay, so here, this is we've done the filtering, and we're looking at three different wave number frequency diagrams. So this one over here, this is frequency, this is wave number, this is the unfiltered flow from the region that we care about. This is filtered in Eulerian space, so at every x, y, z coordinate. And then this is filtered in Lagrangian space. So you can see here, as when you filter in Eulerian space, you're basically filtering the wave numbers higher than F, which is what we wanted to do. But we find that if you filter using the Lagrangian method, we kind of surprisingly get more energy over here in the sort of unbalanced sub-mesoscale range. But this method still seems to be very successful at filtering out energy that's in the sort of internal gravity wave region. So it's not actually super clear to us why this method is not so good at removing these unbalanced sub-mesoscale motions. And so if anyone has suggestions, that would be great.
So you have about 3 minutes left.
Okay, that's good, because I am going to be done in 2 slides. This is the momentum budget. I actually have plotted all of these individual terms, but I've just decided to show you the tendency term, because the other terms are not very interesting, and they don't tend to have any differences between Euler and Lagrangian that are very visible. But so yeah, this is the unfiltered du by dt from the surface velocity field. And so you can see these sort of internal wave motions. I've really zoomed in so that you can see this region is a pretty high velocity region compared with the rest of the domain because of the Gillis current. And so you can see there's quite a lot of high high tendency areas right here. And okay, so this is du by dt when you use the Eulerian filtering. And so you can see it seems to be successfully removing the internal gravity waves. That's great. But actually, it's also removing maybe some other stuff. And that other stuff does seem to remain when we do this Lagrangian filtering method. So where we filter with the velocities from the particles. And so, yeah, to first order, both methods are really successfully removing the internal gravity waves, but the Lagrangian filtering is perhaps leaving some other information that the Eulerian filtering didn't, particularly in these sort of high velocity regions. These are really the most high velocity regions in our domain. Okay, so to get to conclusions, the Lagrangian filtering is supposed to correct for the effects of Doppler shift. Eulerian and Lagrangian filtering of the surface velocity field produce somewhat different results, and that's probably most visible to us at the moment in frequency wave number space. And we really want to understand how these filtering methods differ from each other and how we can better measure the effectiveness of Lagrangian filtering at separating the two fields. Yeah.
Okay, thank you, Spencer. We have time for some questions, and the first one actually comes through the chat. So maybe Jack, if you want to ask the question aloud.
Yes, I was just wondering, so you remap your mean quantities to a point which seems a bit arbitrary. I was wondering what is the connection between that point and what you would get if you were doing generalized Lagrangian mean average, where there's a kind of strict definition for what is meant by the mean trajectory?
I think that, right, we're hoping that the points are sufficiently close together that we're really resolving the whole flow field in the model. Right, you know, at some stage you could put more particles in, but you're not getting any more information. So I think.
I guess my question is, can you reconstitute a mean flow and you know, a Lagrangian mean flow, and what is the definition of that Lagrangian mean flow?
I mean, yeah, that's not what I'm trying to do. I think that that's a framework I'm interested in, but I haven't really looked at it. This method really focuses on the particles, but they're being advected by the total flow, right? So, yeah. But
I guess you can take your mean velocity and move particles with that.
Yes, that's true. That's true. But I mean, that's not what we're doing because, right, the flow field is changing all the time, and not just because of the waves. So I think that, yeah, the goal here is not to get to the Lagrangian mean velocity. It's to filter in this Lagrangian way.
Okay, thanks.
Okay, thanks. Then we have one question by Roy. If you want to ask your question.
Yes. So, hey, Spencer.
Hi.
Jonathan Gula was sort of just talking about it, sharing this in the chat. But I think there's one possibility to why you're not able to filter out the unbalanced mesoscales, as you call them. And the reason is because you're affecting particles in 2 dimensions. So if your flow is largely geostrophic and horizontally non-divergent, then you're sort of occupying the space without any problems. But once you start resolving submesoscale features, which are not waves, but they can have substantial or convergences and divergences, then your particles would tend to sort of collapse onto them. And so you're not overall sampling your domain in the same way. And so you can have issues because all of your particles are going to concentrate at these fronts and filaments, and so you're not space filling. So
Yeah, actually, I don't think we do have this problem. I think that this is a problem that we've thought about, right, this is why we start our particles on the regular grid and we run them forwards for 36 hours and we run them backwards for 36 hours. And that, I mean, at least hopefully will prevent this clumping from happening. Does that make sense?
You could also affect particles in 3D.
Yes, that's true. Yeah, I think that is a thing to think about, yes.
But maybe it will help, I don't know. But this could possibly be an issue, I guess.
Yeah.
Okay, I'm not sure. We're actually on time now for the break. Spencer, maybe I can ask you to just have a look at the chat, same with all the other speakers, just to see if there's questions to you. There's several ones actually. And also one question from YouTube. Before we go into the break, just a couple of small things. So first of all, I'm posting just the YouTube link again for everyone who's here for the actual YouTube stream. The stream will be archived by YouTube, and we will ask for permission from all the speakers that we can actually then open it to the public. At the moment, you can only enter the YouTube stream via the specific link. No one else can see it in the internet otherwise. And the other thing is we are now going into the break. So you're free to talk in the Zoom, but it will still be streamed. So we're trying to bring up sort of a break slide. So maybe move to GatherTown or use the chat unless you're fine with being overheard by people on YouTube, which we could also then later in the archiving could cut out if necessary. But otherwise, please use also the other methods that we have for chatting to each other, if that's possible. And yeah, one thing, if you don't want to be seen on YouTube, just don't put your video on. So because then it's not transmitted anyway.
Yeah, I'm going to stay here in the chat. And so anyone who wants to talk, I'll be in the chat for this break.
Spencer?
Yes.
Yes, so one comment. So I've been working with a graduate student of mine on sort of operationalizing a method that was originally developed by David Dritchell, which he called optimal potential vorticity balance. We just generalized it and called it optimal balance, which is essentially a numerical way of nonlinearly balancing flows using the model equations that one has anyway. In a nonlinear way, and the only thing that one has to be able to do is to have a linear concept of mode decomposition. But the balancing will be in an almost rigorous way done optimally. Now we have tested that so far for the shallow water equation, so in very idealized model simulation. So my dream is always, and that's also part of sort of the second phase projects in this network that we are having. So my dream is to actually do that on big models. And so any sort of experience or also modeling groups that use different methods like you do would be of great interest to us to have something to compare to, and maybe also have a concrete scenario what to shoot for.
Okay, I mean, yeah, that sounds very interesting. Maybe I'll try and read one. Do you have stuff out about it? No?
We have one paper published, and I can just post. Just hang on, I'll post a link in the chat, so some advertisement. Okay, chat. Okay. So that's this optimal balance paper.
Okay, thank you very much.
Now that is still sort of baby numerics in some sense and small simulations compared to what you are doing. But the point is that in order to do that, all we need is a numerical method in principle, and we need, so what the method does is essentially sort of adiabatically turning off the nonlinear interactions. So what you do is you have a full nonlinear model, and then you run it, let's say, backward in time, slowly turning off the nonlinear interactions. Now, when it's fully linear, because nonlinearities have been turned off, you do your mode projections, which are exact on the linear end, and then you move forward in time again. And in the end, you will end up at the same time level as you have started with your unbalanced flow. But you have a motion that where basically the imbalanced components have been completely removed. And now you can basically ask the question, well, I have, let's say, some data that I believe is true, and that will have been disturbed. So you can run that in a sort of loop where you always restore the things that you want to keep. And what the method is then, if it converges in this sort of backward and forward simulation cycle, if it converges, it will basically reconstruct all the sort of hidden fields that you are not slaving to your data in a completely balanced way.
Okay.
And one can actually prove, at least for very small toy problems, so not in fluid mechanics, but we have some ODE examples where there's actually rigorous theory, and it basically says that if you're thinking about, let's say, balanced motion as an asymptotic expansion, which is optimally truncated in theory, which of course you cannot do because it's too many terms, and it would be an unhandleable mess. But you can show that what you get with this optimal balance method is actually exponentially close in, let's say, the Rossby number to what you would get supposing you could actually optimally truncate the asymptotic series.
Okay.
So it's sort of a completely numerical method to get exponentially close to what would be the best possible solution if you could theoretically do optimal theory, which makes it interesting.
Yeah, I mean, it sounds very...
But we come from the theoretical end, so we have, let's say, limited experience with big simulations and so forth. But that is sort of one of the longer term goals where I want to shoot at, to actually do this for a serious model simulation and see if it still works. So moving away from the toy problems that we've been studying so far.
Great. Yeah, I mean, thanks very much. Let's keep in touch.
Let's keep in touch, because so we won't have anything. So we're just starting this project, and the new PhD student is still in the visa process and hasn't arrived on the ground due to Corona and all that. So it's sort of starting up very slowly, but it's something we want to develop over the next couple of years.
Great.
Okay. Yeah, so thanks for your talk.
And a couple of the chat questions, but yeah, it was nice.
Okay, yeah, and we probably have to leave the Zoom also to others.
Hey, Nico, Roy. This is interesting. This is kind of fun.
Manita?
Yeah.
how am I supposed to do it? So it looked like the previous session, people were given a warning 3 minutes before the 20 minutes, which doesn't really leave time for discussions.
Yeah, so the Makeda talks were 20 minutes and most talks are 15 minutes and 5 minutes discussion.
Okay, good.
And you can choose how you want to do this.
So I'm giving them a warning after 12 minutes then. Is that the idea?
As you please, or after 14 minutes, no, not 14, but like 13 minutes, so 2 minutes before.
Okay, good. Yeah, thanks. So I know.
And we can let you know if there are questions from outside the chat.
Mm-hmm.
So either by writing on the chat or just speaking up.
Good.
You don't have to worry about me, Ulrich.
Hi, Bruce. Good to see you.
Good to see you too.
Mm-hmm.
It's a bit early in the morning for me, but I thank God we just went through daylight savings time, so it's only a 7-hour time difference and not an 8-hour time difference.
Oh, I see. So you're ahead of us.
Hi, Bruce. Long time no see, huh?
Ah, no kidding, Boris. The family back together.
Yes.
It was great to see you too, Spencer. It's been a long time. Great to see you're doing well.
Hello, Bruce. Hello, Ulrich. This is Pascal.
Hi,
I'm
Pascal.
in my bathrobe, so I'm not going to turn on my video. It's very early here. Interesting talks.
Yeah, absolutely. So I guess we begin now. Next speaker is Bruce Sutherland, and I will give you a warning when the 15 minutes are over. That leaves you then 5 minutes for discussion on whatever you subtract for your talk. Good.
Okay. So thanks everyone for being here, and thanks for the invitation to speak. My apologies, first of all, for people who have seen aspects of this work before, but I love the chance to highlight this great work that was done by Lois Baker, who is a fellow of the Woods Hole Oceanographic Institution GFD summer program back in 2019. And so what inspired this, I was trying to run some simulations of internal modes in the ocean and looking at the development of triad resonant instabilities, which I never saw in non-uniform stratification. But I did see this, so I'll just run this simulation. This is showing a mode 1 internal mode, which is horizontally periodic. That's on the left frame. On the right frame, I've done a filter to eliminate the mode and show you everything else that's left. There's an artificial vertical band here, and that's just a result of creating the MPEG. I just want you to notice that the scale of the filtered is much smaller than the scale of the primary mode. So you get this thing running, it's zooming along, and the first thing you see that happens is the primary mode, the parent mode, excites a disturbance that has double the horizontal wave number, half the vertical wavelength. But the thing that's shocking is as time progresses, it fades out and then it comes back. And then as time keeps on going, it fades out again and then it comes back. And it's the occurrence of that beating that I wanted to understand, and it seemed like a good project to give to Lois, who was just a remarkable student who nailed the problem in a short matter of 8 weeks. Okay, so let me dive into the theory here. So we're just going to take the fully nonlinear Boussinesq equations. This is on the F plane, and generally with non-uniform stratification. And all I'm doing is manipulating the equations to put all the nonlinear terms on one side and the linear terms on the other side. So we have that, and then the plan is we look first of all for just the solution of the linear equation to get the structure and the dispersion relation of the parent mode. And so this is the stream function of that parent mode, which will have a vertical structure psi1 hat. That phi is just your kx minus omega t, and some amplitude I'm going to denote by alpha. And then the vertical structure you get after you plug this into this linear differential operator, you get this ordinary differential equation. That gives you the vertical structure, and the eigenvalue gives the corresponding relationship between the frequency and the wave number. Okay, so that's straightforward linear theory. So, for example, let's take an exponential stratification in red. This is what you get for a fixed value of the horizontal wave number k. This is the vertical structure of the mode you get. It looks a bit like, say, half of a sine wave, except because the non-uniform stratification, the peak of that hump is shifted upwards a little bit. And if you do this for a whole range of wave numbers k, then you get the dispersion relation, frequency as a function of wave number. And of course, if you have non-zero f, that flattens out at the value of f over n. So that's just, again, linear theory. So now the plan is we want to look at the parent interacting with itself through the nonlinear terms and see how that drives a superharmonic disturbance. So we know the parent mode structure, we know the stream function, and hence we know the components of velocity, the buoyancy, and so on. We can stick all of that into here, which gives us a prescribed known forcing, and we want to see what the response is. So this is basically what you stick it into here, and I want to emphasize here that I'm only looking at the self-interaction where an e to the I phi interacts with another e to the plus I phi to give us a superharmonic. There is another part which creates a mean flow in e to the 0 phi, and I'll touch on that right at the end of this talk. But let's just work with focusing on the superharmonics. So when you put in all this information with the, using the polarization relations, this nonlinear forcing, the vertical structure is prescribed by this function I'm calling G2. And I want you to notice that this involves a z derivative of n squared. So if you have uniform stratification, you will not see superharmonics. And that's something that's often overlooked when people tend to start off by focusing on uniform stratification. You ignore this effect. So it is crucial that you have non-uniform stratification. Okay, so we're going to look for a solution where we have this forcing and we're looking for the order amplitude squared function that's created as a result. So this is going to be something, again, that's superharmonic, but it will have some vertical structure we have to find. Again, we're looking for the beating of the superharmonic, so it should have some slow time dependence, slow compared, say, with the period of the parent wave, and so on. So how do we find that? Again, this is the structure we're starting off with, and we're just going to do a simple separation of variables assumption where we're going to assume that this response function is the superposition of basically a time dependence acting on a mode 1, a mode 2, a mode 3 of this response. Okay, so we're just going to break it down in this way. And again, these vertical structures of the psi hat, these are just modes of the system for each of mode 1, 2, 3, and so on. So it again satisfies this dispersion relation, or sorry, this ordinary differential equation, except now it's based on a wave number 2k, because that's the superharmonic wave number. And there'll be a corresponding frequency, which we get from the solution of this equation that corresponds to this mode with wave number 2k. And I'll point just from Sturm-Liouville theorem that in solving this equation, we're going to take advantage of the fact that these vertical structure functions are orthogonal with respect to a weight function, which again is a z-dependent weight function because n is non-uniform. So again, here's our problem. Here's our breakdown of this into modes, and this is our use of this orthogonality principle. So we're just going to take our differential equation, multiply both sides by one of these vertical structures, then integrate with respect to this weight, and that will pull out sequentially an ordinary differential equation that will tell us how the amplitude of each of these modes evolve in time. Okay, and so this is what you get. It's a bit of an approximation here. There's two time derivatives in the original equation, but we're assuming that this is slowly time evolving. So you only need to grab one of those time derivatives. So we get this relatively simple differential equation that tells us how the amplitude of each mode evolves in time. And it looks relatively simple, but of course the devil's in the details. It involves the peak of this amplitude involves this mj, and that's that process of pulling out these orthogonal functions. So this is nasty, but it is explicitly known. You can calculate numerically rather easily. So let's now dive in and work out, well, what is this mj and this delta j that appears in this coefficient of aj for each of these vertical modes? So here what I'm plotting, first of all, is in this blue line, this is the value of mj for j equals 1, 2, 3, and so on. And you can see it's negligibly small except for the mode 1. And likewise, this delta j, which appears in the denominator of that previous expression, it's pretty small for j equals 1, and then it becomes larger. And so when you take the ratio of the two, which is the thing that sets that maximum amplitude of aj, It's a huge peak at j equals 1 and absolutely negligibly small for larger modes, which tells you even though ostensibly this forcing is dumping energy into a superposition of modes, in fact, dominantly is dumping everything back into a mode 1. And the reason you can understand these two behaviors, first of all, if you look at doing this integral, the mode 1, so the psi hat 2 comma 1, is just positive signed. There's no inflection point, or sorry, there's no zero crossing. And so this whole integrand is net positive, and that's what gives you such a large MJ. If you go up to the psi hat 2 comma 2, well, that's mode 2 has a positive on one side, a negative on the other side, and so it's going to lessen the value of MJ, and that's why the MJ drops off when j equals to 2, 3, and so on. Likewise with that delta j, the reason it's small initially is if you look at delta 1, well, that's really just taking the frequency of the 2K mode, and you're comparing it with twice the parent mode frequency. That gives you that difference in the denominator. And that's relatively, they're pretty close together if, for example, f is 0.01 n naught. And in fact, if you're at the equator where f is effectively 0, the two almost overlap. So that tells you that delta j is actually getting pretty close to 0, which means the ratio of mj over delta j is going to give you something close to a delta function peak. So a really strong amplitude forcing, which is actually the most important part of this talk for applications. Anyways, let's run with this. So we worked out that really everything's being dumped mostly almost entirely into mode 1. So let's just define that epsilon parameter, which I introduced before without definition. Now we're going to say that this is equal to that delta 1, which we know is small. That's that difference in the frequencies of double the frequency squared of the parent mode and the actual frequency of the mode 1 with wave number 2K. So let's proceed. Again, we have, this is now our parent mode, and this is the structure of the mode 2, and this is how that amplitude evolves. And you can see it's going to be something that at t equals 0 is 0, but then as time progresses, this is going to grow and then decay. And so now we have an understanding of what sets this slow beat frequency. It's really set by our time scale, depending on epsilon times t, where epsilon again is this delta 1. All right, now this is what I still, in my weird way of thinking, think of this as being kind of a linear theory, because we're really just looking at how the parent interacts to create the superharmonic, but we're not looking at the feedback of how the superharmonic then affects the parent. So let's do that next. So now we're going to take our stream function to be the superposition of the parent, which itself now can evolve in time because of that feedback, and the superharmonic it's creating. And so before, what we had was this four ordinary differential equation where this parent mode amplitude was constant. Once you make it allow this to vary in time, really more generally you account for that variation in time by putting in a p squared there. So that's the easy part. The more difficult part is actually working out how the parent mode changes in time. Now we're looking at interactions between the superharmonic and the parent pulling out the e to the minus I phi, so it plops back into an e to the I phi. Of course, we could also an e to the minus I to I phi and e to the plus I phi. That also feeds back on the parent. So that gives us this differential equation. Again, we're just plopping in all those products of parent mode linear terms with superharmonic linear terms into those nonlinear equations to get an order amplitude cubed response to the parent. And that's what gives us this. Again, the devil's in the details. All those product interactions in nonlinear terms is given by the script D, which was this ugly mess. Really gross, but again, you can evaluate it. So at least numerically, it's not a big deal. So this is our coupled pair of nonlinear equations that give us the evolution of the superharmonic and of the parent. They have a rather nice conservation law that they satisfy. And furthermore, you can combine them if you define a capital X to be 1 minus the parent mode amplitude squared. You actually get this single ordinary differential equation for how that evolves in time. And then you can do some approximations to it, and you can work out explicitly how the amplitude of the superharmonic, for example, varies in time. It still is 1 minus a cosine in time with some small little variation, depending on this value delta, which involves all these coefficients. So just as a comparison, if we didn't do that weakly nonlinear part, if we just didn't have the parent responding, we would get for the magnitude of the amplitude as a function of the wave number being more or less linear. This correction shows that it tails off. And in fact, that really agrees well with a whole bunch of numerical simulations of what's observed. And likewise, we get a good agreement for the beat period. Okay, so just to conclude, this has basically been just looking at these interactions, how you create superharmonics. And the reason I think this might be interesting, these things are growing in amplitude and then decaying, but I showed you that as you get close to the equator, F gets close to 0, the things actually grow to larger and larger amplitude, and they stay at larger amplitude over a longer and longer time, and that's because the period is set by epsilon times t. So as epsilon goes to 0, these things grow to large amplitude and they stay there for a long time, which tells you then there's a possibility that those superharmonics can then themselves excite even more superharmonics. And now you've got potentially an energy cascade going to higher and higher horizontal wave number. So that might be a process that previously hasn't been considered for the cascade of energy to small scale. And finally, I'm just going to show you this movie. I only talked about the superharmonic generation, but the parent actually can interact with itself to create an induced mean flow, and that's what I'm showing here. So there actually is a whole bunch of wave lengths of a parent mode here, which I filtered out. And this is the wave induced mean flow, negative near the surface, positive near the bottom. And in this movie, I'm just going to show how the mean flow evolves, but in the bottom panel, I'll also have the mean flow and the superharmonics. And you can see that the superharmonics actually have a comparable amplitude to the wave induced mean flow that develops. And because you have this induced mean flow, it can act to Doppler shift the waves. And so you can see as time evolves here, there's a slight modulation happening for these waves in time. And with that, I'll close. Thank you very much.
Thanks a lot. Great timing.
Do my best for you, Ulrich.
So we've got really 5 minutes for questions. Is there anybody who would like to?
Kevin has a question.
Kevin, go ahead.
Hi, can you hear me?
Yeah, I can. You're a bit soft there, Kevin.
So is there a connection to near resonant triads?
So again, the whole motivation of this, I was looking for triad resonant instability, which I do see is stratification is uniform or even top hat-like. But in any simulation where I had exponential stratification, I ran these things for the equivalent of months in real units, say, and I never saw triads popping out. Everything was always dominated by the wave-induced mean flow and the superharmonics.
Sure, but yours...
I know mathematically where you're coming from. We've talked about this in the past. Yeah. So I think you could do a similar analysis, theoretical analysis, to work out, close to triad resonant instability when you have non-uniform stratification. But practically in simulations, I never see it, despite the fact that it was observed in a paper by Hasselwinkel oh God, this is the problem with it being too early in the morning. Winters.
Yeah, but your theory looks very similar to near resonant triad theory. It's just what I'm thinking about. I'll have to think about it some more.
Fair enough.
There's also a comment from Nicolas Crusoir. Nicolas, do you want to speak up yourself, or?
Hi. Yeah, it's very similar to Kevin's question. The solutions qualitatively look like solutions to Manley-Rowe equations, which predict periodic exchanges between modes in triad interactions. And Hasselmann had re-derived them in the 60s for gravity waves. I was wondering if you had tried to compare the formalism and the solutions.
But I haven't.
I think it's the same. Yeah,
it's a good suggestion. Again, the thing is, as soon as I didn't see them pop out in numerics, I figured, well, theory's all very nice, but if I can't see it develop in the numerics, then maybe it just is in the realm of theory. And I want to point out that in the simulations, of course, I needed to have diffusion but this was a spectral code. I set up diffusion so it would only act on the very, very high wave numbers, and it wouldn't act over a very broad range. So diffusion was not what was keeping TRI from developing.
Oh.
And I also know that what I'm saying here is a bit controversial because tons of people look at triad resonance stability in the ocean. And so it really boggles my mind that I don't get it popping out of these simulations with non-uniform stratification.
Okay.
Okay. So I think we should move on now to, and thanks a lot again, Bruce, now to Costanza's talk, Costanza Roda. We'll talk about laboratory experiments. And you also have 15 minutes, and I will give you a warning before at 40 minutes.
Yes. Can you see my screen?
Yes.
Okay, perfect. Okay, great. I'm ready. So thank you very much, Manita, and all the other organizers for inviting me and giving me the opportunity to present my work. And my talk today focuses on 2 laboratory experiments where we can study the interaction between gravity waves and balance flow. So the first one is part of my work done during my PhD with Uwe Hallander at VTU in Cottbus. And we have used the differentially heated rotating annulus to study gravity waves emission from jet and France. And it's more applied to the atmospheric case. And the second part, I will focus on preliminary results that we just obtained from long experimental campaigns in Grenoble, where I work now with in the group of Nicolas Mortin. Okay, so just quickly to remind you what we are looking for in our laboratory experiments. In the atmosphere, you all know very well, we have the large-scale balance flow. And at the mid latitudes, we have here a nice animation from NASA where you can see this jet stream. And it is well known that from this large-scale flow, gravity waves are emitted and are. You can see on the right-hand side of the screen this animation from the model ACMWF, where the divergence field is plotted. So you see these smaller scale gravity waves which travel with the flow and are emitted from it. And this is exactly what we want to model in our laboratory experiment. And to do so, we have here on the left-hand side, you see a picture of the differentially heated rotating annulus, which is the experiment we used in Cottbus. So the principle of this experiment is that we have a tank. In this case, we have a quite large tank, which measures 1.5 meters in diameter. And this tank is made out of plexiglass and is divided into 3 concentric cylinders by transparent walls. All the 3 sections are filled with water. And in the outer cylinder, we warm up the water, and in the innermost cylinder part, we cool it down. And these 2 regions, as you can see from the sketch on the right-hand side, represents the equator and the pole regions of the Earth, respectively. So the mid gap, which is the region we are interested in, is subjected to a radial difference of temperature imposed by the thermal conduction at the walls. And also, we rotate the tank. So we have 2 elements, which are the difference of temperature, giving us a stratification in the fluid, and we have rotation. And these 2 elements give us the baroclinic instability, which is the analogous of the large-scale flow. And I want to stress here that we don't mechanically force gravity waves, but we just force the baroclinic waves here, and we see whether gravity waves develop from the jet. And this is exactly what we find out. So this is on the left-hand side, you can see surface temperature map. So we have an infrared camera, which is recording the temperature from the top of the tank. And you can see that it looks a very regular baroclinic wave pattern, which mimics the jet in the atmosphere. And in these small windows here on the left-hand side, we used PIV technique, which is a rather common laboratory technique to obtain horizontal velocity components in our case. And you cannot see, but there are these small arrows, which are the velocity. And then on top of that, the color map shows the horizontal divergence. And on the right-hand side, we have an animation to see how this horizontal divergence evolves in time. And you can see nicely that we have some gravity wave strain features that move along the jet, which is marked by this streamline. And the crests are mostly perpendicular, oriented perpendicular to the jet. And the velocity of the waves is comparable to the velocity of the jet. So they are mostly advected by the jet. And in this situation, what we can do is we can study the energetics of this of our experiment. So here we have the kinetic energy spectra, and I plotted on the left-hand side we have the experimental data, and I plot for comparison the atmospheric spectra from Armstrong and Gage. And you can immediately see that there is a resemblance between the two. And in particular, we have these two slopes well visible in the laboratory as well, where we have a larger scale part with the k to the -3 slope, and a smaller scale part transition to a k to the -5/3 part. And this part also corresponds to, well, I should specify that this is a frequency spectrum, but because of the particular properties of our flow, we can make a Taylor assumption and then convert it to a wave number spectrum. But anyways, what I wanted to underline is that in this shallower water part, we are in the gravity waves wave frequency. So now what we can do is apply a decomposition method, and we use exactly the same method that you heard before in Jacques' talk. So this spectral decomposition method developed by Callies, Ferrari and Bühler, which is very convenient because it has been developed for decompose observational data and from aircrafts or ship tracks. And the main point, the main advantage is that it only uses the two velocity spectra. So we have CV and CU, and so we can retrieve a decomposition even in case of experiments where we don't have the full 3D field. So in a nutshell, this method applies first a Helmholtz decomposition, where we can find the rotational component and the divergent component. And the second step is a wave vortex decomposition based on the assumption that the total energy is just given by a geostrophic part and a wave part, and these waves are linear inertial gravity waves. And if we further assume that they are in hydrostatic balance, the vertical part, which is this SW, is negligible, and so the wave part is simply 2 times the divergent component, which is very simple to apply to our data. And if we apply this decomposition, what we find for our energy spectra is that indeed, similarly to the atmosphere, we have the black line here is the total energy, and then we have the blue part, which is the gravity waves component, which dominates at this -5/3 shallower part of the spectrum. And instead, for the larger scales, we have the geostrophic component, which is dominant. So to conclude this first part, I've shown you that the first experiment with the differentially heated rotating annulus, which captures well the jet stream and gravity waves dynamic. And then we studied the energy spectra, which reproduce very well the atmospheric ones. And in our case, we found that gravity waves dominate the shallower part of the spectrum. Now I will switch to the second part of my talk, and I will present you some experiments that we have done in Coriolis. And for those of you who don't know, this is a huge experiment here in Grenoble, where we have a 13 meters diameter tank. And here in this picture, you recognize a person to give you the scale of the system. And in this case, we use, just for give you some numbers, 130 tons of water. And this tank can rotate up to 6 RPM. Or in this case, we have a stratification given by salinity. So we prepare a linear stratified profile. And what do we do with this experiment? So this is a schematic of the tank, and inside it we have built a pentagon shape where we have one fixed wall and 4 other walls which can oscillate. And here is a sketch of these oscillating walls where we can move the walls around their mid-depth point. And in this way, by changing amplitude and the frequency of the forcing, we we force gravity waves in this system. And also, again, we have a PIV system here where we can measure horizontal velocity in this small, which is not so small, window at the middle of the domain. And also we can do a vertical PIV. Just to give you some parameters, the typical stratification is 0.45 rads per second. And we have done an experimental campaign where we have different forcing frequencies varying from 0.15 to 0.7 N. And we have done experiments both with rotation and without rotation. So some preliminary results. First of all, I want to show you what happens when we force the waves. So this, I'm going to show you a movie just taken with the camera where you will see the particle in the water, which are used as tracer. And you will see the evolution of the flow. And this is accelerated 50 times. So as you can see here, at the beginning, we can really see that we have the large scale forcing and the frequency of the forcing. But as soon as we move further in time, we have the appearance of smaller scales. And you can see that we have also higher frequencies appearing. So the system transitions to a state where we can see that we have smaller scales arising from our forcing. And what do we have in our flow? The interesting thing is that both with rotation and with non-rotation, we have a large scale vortex, which is plotted here. Here we have 2 snapshots of the velocity at 2 different heights. We have small arrows, so I hope you can see that here they are rotating counterclockwise, and further down they are propagating clockwise. So we have a change of rotation direction with depth. And you can see it very well here in the plot of the average vertical vorticity. So this is the large scale flow that we have in our system. And then on top of that, of course, we have the gravity waves that we force. So we have done a study for different amplitude of forcing and for these different forcing frequencies. And the interesting thing is that if we force with a large enough amplitude and with high enough frequency, we have a transition from discrete modes and only wave interaction to a cascade, which is visible in the spectrum. So here I'm showing you the spectrum for a typical spectrum for experiment with no rotation, where you can see we have this for spectrum again. We have for large frequency, we have for small frequencies, we have discrete modes. And then we have here a peak at the forcing frequency. And above the forcing, we can see a cascade, and which has the slope of omega to the -2 and goes beyond n, which is here in this line shown here. And very similarly, in the case with experiments with rotation, we have, in this case, we have a lower bound for gravity waves, which is given by F. So we have between F and N gravity waves. And then again, for frequencies higher than the forcing, we have this typical omega to the -2 cascade. And for the, we have then also a large scale geostrophic flow, but we have to further investigate that. And I just want to point out that this spectra looks qualitatively for the moment very similar to the ocean spectra, where we retrieve this typical omega to the -2 Garrett harmonic spectrum. But there is still, this is really preliminary work, and we have a lot of data to analyze, and we will further investigate waves interaction and wave flow interactions. And so to conclude, I presented you in this second part, the large-scale Coriolis facility that we use to study gravity waves, which are in this case mechanically forced. And we have a flow that was made by a large-scale vortex and inertial gravity waves. And we have seen that for large enough amplitudes and high enough frequencies, which, by the way, is meaning that we have a large enough buoyancy Reynolds number, we observe a transition where we have a cascade to omega to the -2 slope, which looks very similar to the atmospheric spectrum. And with this, I thank you for your attention, and I'm happy to take questions.
Yeah, thanks a lot. Also perfectly timed, so there is a lot of time for questions. Carsten? We don't hear you.
No, it should work.
Yeah.
Thank you for this nice talk, Constanza. But I want to challenge a little bit the first part, actually, and Ulrich maybe can also comment on this. When we do these experiments of baroclinic instability in models, we also see some structures which look like waves, as you do in the tank. But if you look in closer, then there are no waves, but these slaved modes. So, but I also understand that it's very difficult to diagnose this in a tank already, and it's even more difficult to do spectral analysis as we do for numerical models. So this is more like a comment. And I think Manita will also tell a little bit about the story in the next talk.
I'm very well aware. Unfortunately, experimentally, we have only access to a 2D flow, so it is very difficult to work on more complicated decomposition. We do verify that these waves are what we can verify is that the signal satisfies the dispersion relation of gravity waves. So that's why we say that those are gravity waves. But yeah, I realize this is a very experimental method.
I think there was a question from Boris. And
all right. Thank you for interesting talk, Constanza. I'm going to challenge your third conclusion. You're saying that amplitude that you observe omega to -2 slope in spectrum for both cases with and without rotation. How about the amplitude of the spectra? Are they the same amplitude or the amplitude are different?
Do you mean, what do you mean by amplitude of the spectrum? The spectral density is the same?
Spectral amplitude, no?
Yeah. We haven't looked at that, and yeah, I am not sure these scales are actually correct. So I will have to take a look at that.
All right, you know that the slope by itself is not enough to judge the physics. You need to know.
Oh yeah, absolutely. I'm just saying this is very preliminary work, and we observed that. So I just say that for more. I'm sure it's more a qualitative agreement for now, I would say.
All right, thank you.
Han Wang, had a question?
Yes, so very nice talk. So I just have another challenge for you. So in your first experiment, the BTU one, after you do the Helmholtz decomposition and the wave vortex decomposition, in the spectral plot, I see like the wave part only spans over like the faster frequencies, right? So is there a reason for that?
Yes, so this decomposition works in the assumption that we have special isotropy, which is not true for our case. And there is a further method that they developed where anisotropy is included. Unfortunately, it doesn't work for our data. We tried. So in that case, we could have probably an extension in the in this part of the spectrum. What we are very satisfied is that actually you can see that there is a good portion that shows that we have a separation even for the larger, so for this -3 slope.
So you cut this off because you know there is.
Oh no, we don't cut it off. Sorry, there is there is simply in the calculation here we have an imaginary part. So yeah.
Oh, okay.
Yeah.
Okay. Mm-hmm.
Okay. So I think it's time to move on now to the next speaker, who's our conference organizer, Manita Chuksi, and she will speak about gravity wave emission and balanced shear flow. And yeah, we have a chance to keep on discussing this issue about balanced and unbalanced.
Is my screen visible to everyone?
Yes.
Okay. Okay, then I think I can start talking. I'm sorry, I need to fix something on my screen. Okay. Okay, welcome everyone to my talk. I'm going to talk about gravity wave emission from by shear instability of balanced flow. We already had several introductions now before my talk about balanced and unbalanced motions. So I will only say that here balanced motions are defined to be the ones that exhibit a balance of forces, such as geostrophic balance, and examples are mesoscale eddies in atmosphere and ocean. Unbalanced motions, on the other hand, are the ones which do not exhibit any such balance, and examples are internal gravity waves. A mechanical example to illustrate the interactions between these two motions is a spring pendulum system. So the motion of the pendulum is slow, which is analogous to the balanced flow in geophysical flows, whereas the motion induced in the spring due to the motion of the pendulum is they are high frequency, fast oscillations, much like internal gravity waves. So the coexistence of these two processes and the nonlinear interactions between them make it complex to separate and characterize them, which is why we need flow decomposition methods. So here I am just showing, so there are several methods which we have also seen earlier and we may see in the next talks too. But these are the methods which are based on nonlinear normal mode initialization. And we have implemented them in a series of papers, but here I'm going to show our latest work. So beginning with Mackenhauer, which was initially developed for numerical weather prediction. And the idea was to initially suppress gravity waves in order to minimize the excitation. This is an iterative procedure, and Leith in 1980 showed that the first iteration is actually equivalent to quasi-geostrophic balance state, which is also the first order in RO. RO is the Rossby number. This can be extended to higher orders in Rossby numbers by an expansion that was proposed by Vaughan, and we're going to use this approach. Here I give an overview of the modal decomposition method using single layer model scaled equations, although we have implemented them also in primitive equation models. So here you see equations of U and H. The symbol for U indicates counterclockwise rotation of U by 90 degrees. So when we go on to Fourier space, we can collect all the linear and nonlinear terms together. So here Z is the state variable which contains the state, the U, V, and H from these equations. Matrix A contains all the linear terms in our equations, and vector N represents the nonlinear terms. So this matrix A can be used to obtain eigenvalues, and we obtain 3 of those. One, which is associated with the value 0, is related to the balanced mode, and the other two are related to the unbalanced mode. The corresponding left and right eigenvectors from these eigenvalues can then be used to make projection back to the state vector to obtain the decomposed modes from the flow. So the modal representation then takes the following form, where I here are the interaction coefficients. And yeah, it's described in this way. You can see the term here for the balanced mode, here for the unbalanced mode, and here are the cross interaction terms. Now, we saw in the equations the parameter Rho, which is the Rossby number, and now we can do an expansion in Rossby numbers. So this is based on the approach by Vaughan. I think it was also implemented by Kafiabad and Bartello. So this is based on weak interaction assumption for weakly growing waves. You can see here expansion in Rossby number. And we introduce a fast and a slow time scale. The slow mode then varies only with the slow time scale, whereas the fast mode or the unbalanced modes have both the time scales, the fast and the slow. And then the modal representation takes the following form. This can then be expanded. This can be written out for different orders in Rho, and we can have slow mode and fast modes for different orders in Rossby number. To suppress the wave generation, we can set the time derivative of the fast modes to 0. And this actually is related to the slaved modes. So you will always see these components appearing in the description of fast modes, but they are actually tied to the slow mode, which is why they're called slave modes. The first order slave mode that we obtain here is actually equivalent to the method of Mackenhauer, the first iteration of Mackenhauer, which is nothing but a quasi-geostrophic balance state. So now we implement these methods into beginning with a classical Eddy case, which is about having a zonal flow in a channel with vertical shear. So this is the mean state shown here, so zonal velocity. A perturbation is applied to this mean state, and after linearization, we get growing modes. So here, this figure shows the growth rates. So this is all scaled with Rossby number, and this on the y-axis is the meridional wave number, and on the x-axis is the zonal wave number. And we can see these different growing modes, but the maximum growing mode occurs at about kx equals 1. And this mode is slow and balanced and related to the quasi-geostrophic mode and corresponds to the classical case of pyroclinic instability. Now the potential vorticity of the mean state, which is given here, described here, this is again based on the scaled equations. Note that n and f are set to 1 here. And this is done for different Rossby numbers, as is shown here. And for the combination where Rossby number is 0.5 and U0 equals 2, this term actually vanishes. But when we go to higher Rossby numbers, we can actually see that potential vorticity begins to decrease and even becomes negative. And this satisfies then the condition of symmetric instability. And this is where ageostrophic instability begins to be related to symmetric instability. So this was Eddy-like mean flow. And now we go to a little bit more realistic or complex state where we add also lateral shear, and then we have a jet-like mean flow. So this is again the mean state of such a flow. And now we actually have many more modes appear than we had in the Eddy-like case. So first here, these set of lines here show the growth rate, again with the zonal wave number. The red one corresponds to the QG state. And we can see that the growth rate, the maximum growth rate now occurs at higher zonal wave numbers. So, and if we move to higher Rossby numbers, increasing Rossby numbers, you can also see many more unstable modes appearing, which have high frequency, so they are fast. And they also have not only positive, but also negative frequencies, which you can see here. The white circles here they indicate the eigenvalues at frequency 0, which is equivalent to geostrophic unstable mode. Yeah, and I forgot to mention that here the x-axis is the frequency and the y-axis is the zonal wave number. So now we take these eigenvalues, the eigenvectors associated with these eigenvalues, and use the method by Vaughan and expand and use the balancing procedure up to second order. And then we use this balanced state to initialize the model. So now these are the simulations from such a state when it is initialized by second order balanced QG unstable mode. So what I'm showing here is a vertical velocity. On the top is the actual vertical velocity, and below is the first order balanced mode vertical velocity. So it's scaled with of the order of Rossby number, and the time step is chosen such that this is right after or soon after the onset of baroclinic instability. You can see the meandering of flows very well also in the vertical velocity, but what you do not see is any difference in these in the upper and the lower row for any Rossby number, which means that there is hardly any gravity wave emission up to first order seen here. Now we go to higher orders. The first row here shows the difference of the actual velocity to the first order vertical velocity. And we interpret this as the residual signal of the flow. The lower row shows the second order, the vertical velocity associated with the second order balance mode. Now, the first column here associated with Rossby number 0.1, again, is identical. There's barely any difference. But differences begin to appear for Rossby number 0.2, which are even more prominent if you go to Rossby number 0.3. Meaning that if we have such a flow initialized with the second order balanced QG state, we can see gravity wave emission, but at second orders and at large Rossby numbers. Now we use a different state to initialize these models. We use a state which is closer to the ageostrophic instability mode. Again, on the top is the actual vertical velocity, and below the one associated with the first order balance mode. And in the first column, again, there is hardly any difference. There's little difference appearing for Rossby number 0.2 and much more for Rossby number 0.3. But this is the first order. So if you have initial condition closer to ageostrophic instability mode, we see gravity wave emission already at the first order. But yes, again, for large Rossby number. I am actually now at the summary. So I have given a short overview of the nonlinear decomposition of balanced and unbalanced motions, which is achieved and implemented in in nonlinear models in different dynamical regimes for a range of Rossby numbers. The literature related to methods and the implementation is here if you're interested. The figure here shows the normalized distribution of potential vorticity for different Rossby numbers. So the blue indicates Rossby number 1, and you can see the values are mostly positive and larger. For Rossby number 0.2, we actually begin to see that the smaller values are smaller, but not yet negative. But as soon as we move to Rossby number 0.3, the smaller values become even negative and satisfying the condition of symmetric instability. So we have seen that ageostrophic instability coexists with baroclinic instability mode. The growth rates increase with smaller q and for larger Rossby number. The shear instability of balanced flow emits gravity waves when the condition for symmetric instability is satisfied. For large Rossby number, we see it prominently. And spontaneous wave emission by shear instability is negligible. Thank you. I look forward to your questions.
Thanks a lot. There's a lot of time for questions. Again, great timing. Let's see whether there's anything in the chat. Doesn't look like it. So if nobody else has anything to say, I might ask my standard question. The decomposition between balanced and unbalanced is looking merely at the linear dynamics you have on the left side of the equation is linear dynamics without a mean flow. And in the oceanic context, to my understanding, although I'm not an oceanographer at all, that is probably something you can do quite well in the atmosphere. Actually, the mean flow is pretty strong, and the waves are developing on the background of that mean flow. Which might make decompositions like what we've heard about the Lagrangian decomposition interesting. Do you have any comments on that? Do you think this is straight away applicable to also the atmospheric context?
You mean the one that I do here?
No, I mean what you're doing.
Yeah, I cannot specifically talk about atmospheric context of like the conditions you mentioned. So I know a little bit more about ocean than I do about atmospheres. But in principle, I would think if you change the parameters, it should be applicable, because this is essentially, I mean, we have chosen parameters for ocean, but I would think this should also be applicable to any rotating stratified fluids. I mean, then maybe you get different results, or hopefully not qualitatively, but yeah.
Might perhaps be an interesting check to do.
Sign as a question.
My question is more a question about Ulrich's question. So I didn't understand what's missing. So what Manita was presenting was taking into account some nonlinear interactions as well, but in form of like slave modes. So what you think is like substantially missing here, I really didn't understand. So it's not just based on the linear part. Some nonlinear terms are somehow incorporated.
That's true. I don't question that. I'm just wondering whether when you start decomposing the flow into gravity waves and the rest, then whether, as an atmospheric scientist, the linear terms which would be to leading order describing the gravity waves have strong Doppler shifts involved typically, and that Doppler shift is highly variable also in space and in time, and that makes it maybe more complicated. So my standard picture is always take a mountain wave excited by steady flow over a mountain. That would be something which is steady. So in that concept, if I understand it correctly, would be a balanced flow, but it's a gravity wave. And so, yeah, how do you solve this problem?
I think the only key to differentiate the waves from the balanced flow is the time scale, right? And here the basis, the assumption is that there's a slow time scale and a fast time scale. That's where the method is based on, right? And if the Lee wave is a standing wave, then the time scale is very small, right? So it's a balanced part of the flow.
Right. Okay, but then that is something, at least for atmospheric scientists, these are gravity waves which have an impact on the large scale flow and so forth. And I think nobody would say that's not gravity waves. They are. Yeah, okay, but maybe that we're getting philosophical here.
I just want to say something about the Doppler shift that you mentioned. So now I don't know this here, but the earlier method that I used, when I did the spectra, frequency wave number spectra of these decomposed modes, then we also try to put a Doppler shifted range there. So you can, the dispersion relation, the actual dispersion relation is kind of broadened because of the Doppler shift. So you will see more motions fitting in this Doppler shift, and then some are also below F, below the inertial frequency. I've not shown this here. I've also not done a lot of spectra here, but Yeah, I mean that we also assume a constant mean state, of course, and I think it probably can be extended to complex states, but these methods are already complicated, and doing it in complex models make it even more complicated. But as you said, it would be exciting to approach them sometime. Maybe try to do them.
Can I comment on the last point on the slide here? Manita said, you said spontaneous wave emission is very small in this model. What you mean by this is that there's spontaneous emission by light in the sense of light radiation, right? That is very small. Light radiation would be like if there's only Rossby waves and they emit just spontaneously the gravity waves, like similar to light radiation. And this process we don't find in any model. There is no spontaneous wave emission by similar to light radiation. And what you need is a large Rossby number such that you get small potential vorticity and symmetric instability and all these ageostrophic instabilities, which then can generate the gravity waves.
And the other thing that I also did not mention was that the ageostrophic unstable mode that we see here is actually similar to what we get from MoleMaker. Yeah, and we see also in other simulations that spontaneous emission is not so dominant as convective and symmetric instability.
Okay, thanks a lot. And I think we have to move on now to the last speaker of this session, who's Hossein Kafiabat, and he will talk about wave averaged geostrophic balance.
Can you see my screen?
We do see it, but it's dark.
Okay, dark.
It's black.
Let me try again.
It was visible momentarily.
Is it visible now?
Now it looks much better. Yeah.
All right. Thank you very much for giving me a chance to talk. We're having a wonderful weather today in Edinburgh. I don't know how Jacques was giving a talk in sweater, but it's a t-shirt weather to me. I'm going to talk about wave average geostrophic balance, and this is my work with Jacques Van Est and Bill Young. And I want to talk about the cases where geostrophic balance is not good even at the leading order. So I apologize at the beginning because the first few slides I'm butchering the mathematics, so I'm treating things very loosely. Also, I'll talk about the most basic concepts in GFD and drive it, which is geostrophic balance, not even QG. So if you look at the non-dimensionalized horizontal momentum equation, we have something like this we're all familiar with. And there are some other equations describing the flow. So I assume they just tag along and go through the same procedure. So I use these scalings, and as we are familiar with, the epsilon or Rossby number defined like this here shows up before the nonlinear terms, and I kept my time scale as capital T there before making any assumptions. So I want to say why in certain cases all classical balance models are not good. So the key idea for classical balance models are two assumptions. One is there's two time scale. Manita talked about it in details. And the other one is we can assume that all our flow variables at the leading order are slow. So if we have two time scales, the first term has only slow time scale, and then all other terms are order epsilon smaller. So both of these assumptions are quite essential for most of the balance terms we are familiar with. And based on this, we can just create two time scale. One would be something like eddy turnover time scale, and then for the slow time, and then for the fast time, something like 1 over wave frequency. And then whenever I use over bar, I just mean averaging on fixed spatial point and over the fast time scale. So if I average my variables the average of the fast term is basically 0. So what we do to get balance models, and the most basic one, the geostrophic balance, first we divide our time derivative to the slow and fast time derivative, and then I replaced my characteristic length time scales with L over U, and I get Rossby here, and then get omega, the wave frequency, over F for the fast time derivative. And then in the next step in the process is taking time average, and then no matter how big this term is or how small, the time average of the fast terms are always 0. So these fast terms are basically waves or other types of dynamics. So I interchangeably refer to them as waves. And then for the linear terms, we get just the slow component of the flow. And for now, we can just keep the nonlinear term as they are. And then we keep the leading order, and these two first terms are order epsilon, and we wind up with geostrophic balance. Yeah, great, Hossein. You drive geostrophic balance for the experts in GFD here. But what was the point? Before going to the point, I want to mention all higher order balance, for example, is the ones Manita talked about, and I spent most of my PhD working on them. They just expand the slow terms in terms of Rossby number and keep other terms, and then go to higher order terms in the equations. If we do so, we get, for example, QG balance, QG dynamics at the next order, and we can go on. But the point I want to make here is no matter how far we go, how high in order we go, the leading order does not change. With these assumptions, the leading order is always geostrophic balance. But if we relax one of those assumptions, what if, so if you remember for balance model, we had two assumptions. One was separation of time scale. The other one was assuming that the flow at the leading order is slow. If we relax one of them, what if a fast or wave component is not an order epsilon smaller than the slow component or the balance component? And I want to talk about this particular case here. And for illustration purposes here, I'm just assuming that the fast component or the wave component is order root epsilon bigger than the slow, 1 over root epsilon is bigger than the slow term. It doesn't have to be, it can be the same order, but you will see why I picked this. But the whole message is quite general, doesn't have to be this scaling. So if you do the same thing, but with this assumption now, this new assumption, we take the time average again. Linear terms will be just the slow components, no matter how big the fast component is in time averaging, they get filtered out. Same with the time derivative. But here with the nonlinear term, we have a different story. If we unpack nonlinear term and write it in terms of slow and fast component, we get something like this. So for the slow components, this is order epsilon. For the next two terms, which it has like one slow and fast mode interacting with another, it's order root epsilon. But the last component here, epsilon cancels with two root epsilons in the denominator. So this will become order 0 or order 1 or order epsilon to the power 0, which can compete with the geostrophic balance terms. And this is a quadratic term, so it stays even after time averaging. So what I try to show is even at the very, very leading order, geostrophic balance is not good here. And we get this extra term, which I called it feedback, wave feedback, which is affecting the new form of balance. And this happened because the waves were very strong. Their amplitude were not order of magnitude smaller than the mean flow. So I agree with most people that, yeah, the classical balance models are good because At larger scale in the atmosphere and the ocean, the flow is predominantly slow. But there are regions and there are seasons in geophysical flows that the waves are strong. Either are the same order as the flow, and in some cases they're even stronger than the flow. Another good evidence that this is a very important dynamic is looking at the frequency spectrum of the ocean that you saw in a couple of talks already. And you see a peak close to F, so it means that the near inertial waves are very strong and high amplitude component of the ocean dynamics. And as I tried to show in my first few slides, classical balance models come short of explaining the flow wave interaction in these cases, and we need the wave average models. To explain wave average models and then verify one of the key claims, I start with a very, very simple setup, and I don't make any assumptions in my simulations. I let Buzyn's equations lead the way and see if they agree with wave average balance. So I'm considering an inertial wave, a planar inertial wave, doesn't have any horizontal structure in this form, so it can be written as amplitude times like a cosine and sine of a phase, and phase is vertical wave number times z minus ft. So these are vertically propagating inertial waves. And then I add this to a barotropic axisymmetric anticyclone, and just as a random choice, I picked a Gaussian vortex. So the vertical vorticity of this particular anticyclone, which is axisymmetric and barotropic, has this form. Let's see what happens to this flow when it evolves under Buzyn's equations without any assumptions. So I'm showing here a horizontal slice of a flow. So in the background, you see the vertical vorticity of the flow, and these yellow arrows are the wave velocity. So waves didn't have any horizontal structure at the beginning, so they're quite uniform and change in time. But eventually, if we look at the center, we see that the velocity of waves are changing. Their phase changes from the rest of the plane. Also, their magnitude changes. Somehow they interacted with this vortex, and the wave dynamics is somehow coupled with this balance dynamics. Yeah, you can see that these yellow arrows at the center are considerably bigger than the arrows far from the vortex. The thing is, this fast inertial oscillation is obscuring the slow dynamics, so it's really hard to really see what is happening. And averaging over an inertial period or fast time scale will remove them. But even after in time, we assume that the waves keep this kind of dynamic. So they have the fast and slow time scale, but their amplitude is just slowly evolving, and they have this phase that has a fast time scale. For this particular type of flow, I can replace the time averaging, that bar that I had at the beginning, with vertical averaging, because the vertical dependence show up in this theta, or the phase, that can be removed by just vertical averaging. The leftover, which is the baroclinic part of the flow, would be my wave components. So here, barotropic baroclinic decomposition is the geostrophic wave decomposition for me. And then if I want to look at the slow dynamics, I look at the quantities that are averaged over this theta or phase. One of these quantities is the wave kinetic energy, because if you calculate it, this theta will be eliminated because we have like cos square plus sine square. So now let's look at this video where I'm showing the barotropic vorticity, which is like my time average flow, and I'm showing a wave, a phase average quantity of wave. So it's kind of like the slow part of the wave. And if I look at it in time, you can see, so at the beginning, the wave kinetic energy was uniform, but starts getting concentrated at the center of the vortex and then spreads back into the domain. And if you pay attention, this vortex is also changing a little. It's just, it didn't stay as put. And if there was no wave and there was no interaction or wave feedback on the flow, we were expecting the vortex to stay steady because it's in geostrophic balance. To see this better, I just removed the initial vortex profile from the barotropic vorticity. So I'm just showing the barotropic vorticity anomaly next to the wave kinetic energy. So we can see that actually, yeah, this is the part that is the wave feedback on the flow, and it's substantial, and it's somehow correlated with the wave kinetic energy and has a slow dynamic. So what we saw in those movies was this wave kinetic energy was concentrating inside the anticyclone, and the balance flow got modified by the wave feedback. And these were somehow correlated. Our goal here is to modify classical geostrophic balance to capture this wave feedback. So we basically want to exactly find that wave feedback and a relationship between this wave average quantity and the balance flow. Without going into details, there are some classical results that...
5 minutes left, including discussion time, just to let you know.
Okay. So they claim that even for the case of strong waves, the geostrophic balance holds, but instead of just averaging at each spatial point, if we average over the trajectories, or let's say Lagrangian average, the flow variables, the geostrophic balance still holds, but not for Eulerian averages, for Lagrangian averages instead. And we can write down the Lagrangian average quantities as a sum of the Eulerian average plus these extras, which we call them Stokes term. And the story is a bit, so this is a very classical result. You can see some references there. We offered a simple derivation and then tried to verify this claim in Boussinesq simulation. So if you go back to our Eulerian average quantities, basically in the new balance, in the old balance, geostrophic balance, we just had pressure gradient being balanced by Coriolis force. Now this extra term shows up, which is Stokes Coriolis force, we call it. So now we have balance between three forces. We can calculate these Stokes terms for very easily for the near inertial waves, which is the case of our simulation, and they're very important in the ocean. And we find that they're basically the derivatives of wave action, which is simply wave kinetic energy divided by frequency. And if we write our now generalized geostrophic balance for vertical velocity, vertical vorticity, we get something like that. F times Lagrangian average vertical vorticity is equal to the Laplacian of pressure. So recall that the geostrophic or classical geostrophic balance was just F times Eulerian average zeta is equal to the Laplacian of the pressure. Let's just see actually if you can see this in Boussinesq simulation. Now I'm showing you a profile of vertical velocity, F times vertical velocity. One is time average, Eulerian average, and the other one is Lagrangian average. And also I'm showing the pressure gradient. We can just forget the difference between these, the red lines and the dashed black, because we don't have time to discuss it. But as you can see in time, my Lagrangian averaged vertical vorticity times F, which is these blue stars, are very close to the Laplacian of pressure, but the Eulerian average vertical vorticity is no longer in balance with the Laplacian of pressure, which shows how how powerful this type of balance is. We can also use How much time do you have, Ulrich? Maybe I can skip this part.
You have to unmute yourself.
Yeah, sorry. 1 minute left.
Okay, I'm just gonna skip this part. But in short, I can say, so we can also find the wave feedback from theoretical results, and then calculate the evolution of vertical vorticity. And our theoretical results match very well with the Boussinesq simulation. So my conclusion, I tried to show that wave-induced correction to geostrophic balance really matters for the case of strong waves, and for near inertial wave can be well estimated from wave energy. We also verified a theoretical claim that the geostrophic balance holds in the presence of strong waves for Lagrangian mean velocity and buoyancy. And maybe this is a bit of a flashback to previous talks about satellite altimetry and stuff. We need to be also in our observation, the Stokes terms or the corrections to Eulerian average terms is not negligible. So if you want to estimate velocity from sea surface height, we need to be mindful of the fact that geostrophic balance in Lagrangian sense holds better. And these are some references if you are interested to know more about what we did. Thank you very much.
Thank you. There is time for 1 or 2 really short questions. Carsten?
Do you know what happens if you discuss surface waves instead of your inertial waves? Is it also important?
So, yeah, it is also. I don't understand what you're trying to say. On the surface, are they at the same order of importance, or like the Stokes, for example, the Stokes terms that come from, surface waves are at the same order or are like comparable to these Stokes terms that are coming from strong amplitude waves? Is that the question, Carsten?
Right, that's the question. The Stokes
Yeah,
waves.
I mean, we are saying yes. If you look at the order of magnitude, they are probably not as important, but they're still important. And I'm just going to answer Roy in the text messages. Yes, they still assume small Rossby number, but we just don't make any assumptions with for the amplitude of the waves. But again, separation of time scale is very crucial here.
I mean, it could be fun to try and see what happens if you gradually increase the Rossby number of your.
I'm actually looking at these things. It's lots of things fall apart, especially if you have like turbulence simulation that I'm looking at now, because it's like a range of scales and scale dependent Rossby number is changing across the scale. Yes, definitely these things fall apart, but it's really good to quantify when and where they fall apart. Exactly.
Okay, thanks a lot. I think this closes the session. There'll be a break and then we will reconvene at 5 o'clock.
Can I just say one tiny thing? If you want to go to Gathertown, it's a good idea to stop the Zoom audio, and you can do that in the bottom left when you go where the mute button is. There's a little arrow and that says leave computer audio, so you can switch your Zoom audio off, and then there's no feedback in Gathertown. I think that was discussed in the Gathertown meeting. I think you're muted, Carsten.
Hello, Ulrich.
Oh, yeah. I'm just writing to you.
You're writing to me. Did you see my? You saw my
question. Pardon me?
You saw my reply.
Yeah, and I have a follow-up question. The quasi-geostrophic flow, you resolve it, right? Which you're scattering the waves at. So you don't have any parameterization or a subgrid scale model for the QG flow for the.
No, but it's going to be some random field, right? So it's not. You're averaging over that scale as well. So it's only. I suppose it's useful for an unresolved QG flow, right? So you don't know the details of this QG flow. You're just going to assume some kind of statistics, some kind of spectrum, and then there's the net effect of this random field.
Yeah.
So if you tell me, I have a jet stream or something, this is not good, right? Because I want to average over the scale of that flow. So, but you could split in principle the flow into a resolved part and an unresolved part. And what I forgot to say in my response to you is also this scattering parameterization. It has a natural stochastic formulation too. You can think of it as some kind of random walk in wave number space. So you could deal with that with a particle model like yours, where you follow wave packets, and then every now and then randomly wave packets jump in wave number space. Because that's a scattering, right? It's just kind of a jump.
So if I wanted to use something like this in a ray tracer, you'd need a kind of a theoretical concept of what the QG flow statistics would be, and then
That's right. So based on that, then that you would have some diffusivity, and then you could do the diffusion as you would diffuse a particle. Every time step you would decide to move them by a small amount randomly.
Okay.
I think the moderator should start the session now.
Yes, that's true. Sorry, we were chatting about something else. Right. So welcome to this third session. The first talk is going to be by Han Wan. Is she around?
Yep.
Okay, so you can start sharing your screen. I guess you have the right to do that. And it will be on generalizing wave flow decompositions.
Yep. It's actually this title. The original one was too ambitious.
Okay, so generalize the BCF14 method. Okay, go ahead.
Yep, so I'm Han. So I just graduated from NYU Courant last year, and this is a work I did with Oliver Buehler during the last 2 years of my PhD. And here, the BCF14 method refers to this popular paper, which has been mentioned already by a couple of times this morning. So it's published by Buehler, Callis, and Ferrari in 2014. And just a quick recap of the method. The method tries to do two things. First, it tries to tell the rotational and divergent motions apart from observations. And specifically, we just mean that all the horizontal velocities can be decomposed like this, where this is related to a potential function and this is related to a string function. And the reason why we care about this decomposition is because different dynamical components leave different fingerprints on rotational and divergent modes. For example, the QG motion, as we all know, is just weakly divergent, while the near initial waves are like it's as energetic on the potential excited field and the stream function excited field. And then, so that inspires the next step, which is an actual dynamical decomposition that tries to tell the waves and vortices apart. And in BCF14 paper, they assume linear dynamics. So by that, they just mean to decompose the flow into linear inertial gravity waves and geostrophic winds. And this kind of the dynamic decomposition has like many practical implications, as this audience is well known. And the most challenging part of the BCF14 method is that it tries to do both these things on just one-dimensional data. By one-dimensional, I mean that the data is taken only along one spatial dimension. So for example, it can be a ship track, where the ship only takes dimension along its track, which is 1D in space. So this is a sketch of what the method is doing. The input are just power spectra measured along one dimension, which can be either a ship track or like an aircraft track, aircraft track. And these three fields are just a power spectra of the horizontal velocity components and the buoyancy field, which measures the potential energy spectra. And then the first step, the Helmholtz decomposition, just tries to tell the component in the total kinetic energy spectra, the component that's due to the stream function, which is the rotational motion, and the component that's induced by the potential function, which is divergent. And then after the Helmholtz decomposition, in this oceanic data sets, they find that at scales larger than about 100 kilometers, the rotational motion is dominating over the divergent motion. But this doesn't have a clear dynamical meaning, because we can say that the wave components could also have strong rotational parts. So in order to have a clear interpretation of this Helmholtz decomposition, they do the next step, which is an actual wave and vortex decomposition. And the crucial result in the paper was that for linear waves, they find this so-called equipartition segment, assuming vertical homogeneity. So by that, it just means that the total wave energy is just twice of the kinetic wave energy due to the divergent motion. So then they can do the wave vortex decomposition, and now we can see that at these larger scales, it is indeed the vortex that's dominating over the waves. So this method is very powerful because it can do both of these things with just one-dimensional data only. But of course, it's based on a long list of assumptions. And here I list them all. And in this talk, we are going to talk about how to relax this assumption of horizontal isotropy. And we are specifically going to look at that for Lagrangian observations. So just a quick note on what crucial difference between like ship track data and Lagrangian data. So this is a figure for like a ship track campaign where the red line denotes a ship track. And we can see that this is literally in 1D. It has no 2D information whatsoever. But this is a histogram of surface drifters in a drifter campaign, and the histogram of drifter locations. And we can see that the drifters actually, even though they distribute sparsely in 2D, especially at this kind of locations, there are still 2D information nevertheless. So our main goal is to try to take advantage of all this 2D information in the drifters. And so the method will look different from the 1D version. And as a side note, for the 1D version, to include anisotropy, there isn't sufficient information to have a generic flow for the anisotropy. So some assumptions have to be made on how the isotropy looks like. And this is a related work that's published previously. So the way we quantify anisotropy is through the lens of this azimuthal Fourier series, which means any 2D function can be expanded in this way, which is really just a Fourier expansion with regard to the angles. And here the superscript Cn means it's the cosine and alpha mode, and the superscript Sn means it's the sine and alpha mode. And when we say a function is isotropic, from this series expansion, we can see that what we're actually doing is just to truncate this series at the mode of n equals 0. And the way we quantify anisotropy is just to try to estimate different modes, including the higher modes for the statistical quantities we're interested in. And for Lagrangian data, the statistical quantity we're interested in is called the structure functions. And so what are structure functions? So suppose we have these drifters in the ocean, and at this snapshot, suppose we have 4 different drifters denoted by the red dots. And then we can form all these pairs for these 4 drifters. And then for this pair of drifters specifically, if we draw a vector that joins the 2 locations of the drifters, then this vector is called as the separation vector. And the length of this vector is called the separation distance, while the angle is called the separation angle. So from then on in this talk, whenever I use R and alpha, they always mean the separation distance and separation angle, not like the absolute locations of either of these drifters. So we have this separation vector, and then we can also calculate the velocity difference measured by these 2 drifters. And then the velocity difference can be projected onto two spatial directions, one that's along the vector and one that's across the vector. And we denote these components as delta UL and delta UT. And then we assume horizontal homogeneity and stationarity. But that mathematically, we just mean that if we do an ensemble averaging over this term here, then it's not going to be a function of the time. No, and it's also not going to be a function of any of the absolute locations of either of these drifters. It's just a function of the difference between these two drifters here. So we refer to this as the second order structure function for delta UL. And notation-wise, we denote this as DLL, where the subscripts just mean that there are two delta UL terms in the averaging sign. And similarly, DTT means there are two delta UTs here, and DLT means it's a product of delta UL times delta UT. And in case this looks unfamiliar to you, these structure functions are actually directly related to like covariance functions or power spectra. And they are just more convenient to evaluate for Lagrangian data, which makes them popular. So now we are trying to evaluate the different Fourier modes of these structure functions. And the way we calculate these modes is as follows. So suppose we are looking at DLL and we want to calculate the mode at n equals 0 here. And the inverse transform formula just tells us it's related to the original 2D function from this angle integration. And traditionally, when isotropy was assumed, what people are actually doing from this length of Fourier series expansion is that people are just calculating the zeros mode at n equals 0. And what people have been traditionally doing is that people just calculate a sample averaging. By that, I mean that, for example, if we have 5 drifter pairs here, and they have the same separation distance, but different separation vectors. So traditionally, under isotropy, people just calculate the sum of these 5 drifters and divide them by 5. So that's a simple sample mean. But if we go back to this inverse formula, we can see that something is wrong in this approach because it's not actually evaluating an integration over the angles. So instead, we strongly propose that instead of this traditional way to evaluate structure functions, we should instead try to do angle integration. So again, back to this example, this can be simply just a trapezoidal rule, for example, just calculating these two observations and time them by the angle and so on. And you can choose any integration method you like. The point is that you have to do integration over angles, not the integration over like probability density functions, which correspond to the traditional approach. And so now we have this mode. And for all the higher modes, it's very similar. There is just an extra coefficient of cosine and alpha when you evaluate the angle integration here. So now we have all the modes for the velocity structure functions. And now we try to do the Helmholtz decomposition. And by that, we just mean that, so again, back to this drifted pair, the velocity difference can be projected onto these two directions. And meanwhile, it can also be divided into a part that's induced by rotational motion and a part that's induced by the divergent motion. And I denote them as delta UR and delta UD. And they also have their corresponding structure functions like this, where the subscripts R still denotes there are 2 delta URs here, and DD means there are 2 delta UDs here. And then we found out a set of new Helmholtz decomposition formula that can allow for anisotropy in the statistics. And the assumptions we use during derivation are stationarity, homogeneity, and isotropic correlation. So stationarity and homogeneity are like necessary because without these two assumptions, we cannot even define the structure functions. And this isotropic correlation assumption, which means the correlation between the string and potential functions are a function of R only. This may look restrictive to you, but actually this includes the case when psi and phi are uncorrelated with each other. And that uncorrelatedness is actually assumed more often in previous works. So based on these assumptions, we find this set of formula that applies to 2D structure functions. And the way we use this, so the difference between this new formula with the isotropic formula that was derived before are these two extra terms that's circled here. So the way we use this new set of formula is to write them into different Fourier components. So we get this mass of formulas. And the one thing to note is just that everything on the right-hand side here are just the different Fourier modes of the velocity structure functions. And we have already described how to evaluate them in the previous slide using this example. So now we apply this new method to a real observational data set. And this data set is called the Lagrangian submesoscale experiment. It was taken place in northern Gulf of Mexico in winter 2016. And there are more than 1,000 drifters here, and the data flow that we use have 15-minute time intervals. And so just as an introduction on how to use this method, for this demonstration, we include all the observations available in the laser data set. And the first step is to transform these drifter locations into separation vectors. And this is a histogram of the separation vectors from all these drifter locations. The one thing to note is that this separation vector look very anisotropic. So that means that when you are evaluating different Fourier modes, there should be a big difference between the angle integration and a simple sample averaging. So we then go out to the Helmholtz decomposition and reconstruct to the mode up to n equals 4. And here is the ratio between the reconstructed rotational structure function versus the total structure function. And so when the color is close to white, it means it's dominated by rotations. And when it's black, it's dominated by divergent motions. And it makes sense at some parts in this picture, because at these smaller scales, it's dominated by divergent motion. And at larger scales, it's mostly rotational. However, there are these strange parts at the larger scales at around a few hundred kilometers, which seems to say that it's dominated by rotational motion. And we think the reason for this is simply because if we include every recording in this data set, the assumption of homogeneity can be strongly violated. Like it doesn't make much sense to calculate the structure of the correlation between this point and this point, for example. And in the paper, we will, like the work is like more nuanced. We'll divide this into different subregions, or we believe the dynamics is more homogeneous.
So 3 minutes?
Yep. So just a sum up of what I've said. So in this work, we have found first, like to evaluate the Fourier modes, you have to do an angle integration, not just a simple sample mean. And second, we found a new set of formula for Helmholtz decomposition that applies for anisotropic statistics. And then we apply that onto a set of surface drifter observations. And as a final note, this is my slide where all the assumptions in BCA14 was listed. And so these are the assumptions that has been attempted to relax, and the citations are listed here. So none of these generations are perfect. Like even like in my talk today, like we have to assume isotropic correlation between psi and phi. And also you can see that you see a lot of names repeating here. So not many people are actually trying to relax this. So like we will be ecstatic if someone is interested in joining us generalizing the BCA14 method. And finally, just some possible research directions related to this project. Like for example, this approach where we take Fourier series as universally could be applied to other quantities such as like third order structural functions or like relative dispersions. And it looks like it may be interesting to generalize some classic turbulence series into anisotropic versions. And another thing we're interested in is that maybe we can also improve the method if there is also 2D SSH snapshots available that's concurrent with like the ship track or the drifter observations. because the SSH observations can maybe at least provide some information on how the anisotropy looks like. And finally, like in the ship track example I showed just now, the ship was traveling in this straight line, but we never consider the case when the ship actually doesn't take a straight line. So maybe if the ship takes a turn like this, maybe there is still some 2D information we can use in the decomposition. And this is also left as future work.
Okay, thank you. So we have time for one or two quick questions, if anybody wants to. Carsten?
Yeah, thanks a lot for this nice talk.
Thank you.
I have a question. In the old days, actually, when they were deriving this GM spectrum, there were papers about consistency checks on data. If what you see in the data is really a wave, like I think they use moorings or something like this, but they could say, okay, with this percentage or likelihood, I found a wave in the model. Can you also do this with your decomposition method?
Yeah, so it depends on what we have in the data set. So like we said, so I was mainly talking about the Humboldt decomposition, but the original version of the BCF14 can also do a dynamical decomposition into wave and vortices. It's not like focused on like checking if the dispersion relationship holds. It just derives some formulas that can separate the power spectra into wave and vertical components. But for this Lagrangian data set that I used in this research, they only have velocity measurements. So like they don't have any like buoyancy or like temperature measurements in this data set. So that makes this original BCF14 wave vortex decomposition like we cannot work on this because we have to have some inputs that reflect the potential energy. But yeah, if the data set actually includes some indicators of potential energy spectra, then a dynamical decomposition can be done. Another thing about this is that it also assumes vertical homogeneity, which can be violated close to ocean surface. So it also doesn't apply to surface drifters. But yeah, this is an interesting direction that we want to look at, like how to continue on to the dynamical decomposition.
Okay, thanks. So we'll take also a question by Roy. I think Boris, you'll ask your question later on. I think if that's okay.
So thanks. This was very interesting. So I guess one of the interesting things about the data set you're working with is that there's very special events where clearly the divergence part of the flow and the rotation part of the flow are correlated, specifically at sort of ocean fronts. And so, which is sort of a general thing that we find in numerical simulations that resolve fronts, but this is actually one of the best observations of that. And so do you think your method, the way you're allowing for the correlation, is suitable for such thing? In other words, here we have clear indications of a divergent flow that's not a wave. And so
yeah, that's a good question, and I think we don't know much about this yet. But like on this slide, we do allow for non-zero correlations, but it has to be isotropic. And in the paper, we try to generalize this a bit. So in the paper, we note that even if the correlation it takes an arbitrary form, like it could contain like any arbitrary anisotropic components. So even in the general form, this set of massive formula still holds at the mode when at n equals 0. So this kind of formula still works at the isotropic mode, and that could be used for sometimes if it turns out that the anisotropy is weak. So like the Humboldt decomposition is dominated by the isotropic mode, so then we can still use this in the most general case. But yeah, we don't know how to even check this thing in this kind of data set. Like we try to, but cannot find a good way to do it.
You can check it in models.
Oh yeah. yeah, we didn't use model simulations for this project yet. But yeah.
Okay, so maybe Boris can just ask a quick question.
I don't even have a question, I have a comment, several comments. First of all, the structure function theory was developed for locally isotropic turbulence, not for isotropic turbulence. And locally, it goes all the way back to Kolmogorov. And locally isotropic turbulence holds on relatively small scale. So this theory works pretty well. The other thing is that you used the expression 1/2 of Cu plus Cv, saying that this is kinetic energy. This is not kinetic energy. It's one dimension. You take longitudinal and transverse one-dimensional spectra, you put them together, you call it one-dimensional kinetic energy. This is not a correct way to compute. It's not a kinetic energy. It's just a sum of longitudinal and transverse spectra. And number 3 is that your decomposition is designed for two-dimensional flow, but the flow is not two-dimensional, three-dimensional. And relations between structure functions are very different in 2D and 3D flows. So this is my comment. It's not even a question. Sorry.
Okay. Yeah, thanks.
Okay. I think we just need to move on. Thanks, Anne and Boris. So the next talk was meant to be by Jiuli Liu, but will be given instead by Xuanying Wang. Are you there?
Yeah, I'm here. Can you see my screen?
Yep, that's very good. Okay, so the talk is on dynamical decomposition of multiscale ocean motion. Go ahead.
Hello, everyone. My name is Chen Ying from Xiamen University, China. Now I'm going to present our recent work on decomposition of oceanic motions. The co-authors include Zhiyu Liu, Hongyang Lin, and Dimitris. This schematic shows various kinds of motions in the ocean. For example, the large-scale mean circulation, long Rossby wave, mesoscale eddies, dispersive Rossby waves, IGWs, and 3D turbulence. So every time you get snapshots or a time series from the real ocean, it consists of all these kinds of motion. So this raises the natural question: how to interpret the observation and simulation, and how to separate different signals. Here is a list of current decomposition methods, although it is never complete. For 1D, giving one-dimensional observation, we can decompose the full spectrum into geostrophic component and IGW component. Giving four-dimensional model data, we can also use temporal and spatial filtering. Here is an example of Lagrangian filtering, and to accounting for the effect of Doppler shift effect. We can also use linear or nonlinear normal mode initialization. This kind of method isolated balanced motion at first, but then the difference between the full and the isolated part is unbalanced. People also use balanced relation like QT dynamics as a way of decomposition. Here is an example of separating of vertical velocity. This is the balanced part. This is unbalanced part. Provided four-dimensional data, our motivation is to develop a decomposing approach that is rooted in ocean dynamics and to reconstruct the interior flow from decomposed sea surface height. We use this set of simulation. South China Sea is rich in tidal energy, mesoscale eddies, so it is a suitable place for this piece of research. But a subregion in South China Sea is selected just for convenience. This picture shows the frequency wave number spectrum of sea surface height in that box. Clearly, we can identify mesoscale eddies, low mode IGWs, sub-mesoscale eddies, and high mode IGWs. We will try to decompose those components based on their own unique characteristics. For low mode IGWs, they are mostly concentrated along the dispersion relations. For mesoscale eddies, they are of low frequency and a small wave number. This panel shows the vorticity of high mode IGWs plus sub-mesoscale eddies. This is their divergence. For in relative vorticity, we cannot identify propagating signals, and for divergence, it is almost due to IGWs. So we assume that high mode IGWs are almost irrotational. Sub-mesoscale eddies are nearly non-divergent. These physics are our starting point for decomposition. So let's check one by one. And for low mode IGWs, retracing results show that in homogeneous background stratification and mean flow will cause signal to spread in the direction of frequency. So this inspires us to extract bands of signals along the dispersion lines and regard them as low mode IGWs. These 6 panels shows the different variables for the isolated low mode IGWs. For mesoscale eddies, we just do low pass spatially and temporally. Here are 6 different variables. For sub-mesoscale eddies and high mode IGWs, we just use the assumption mentioned above. That is, the total divergence comes from high mode IGWs, while the divergence, the vorticity of high mode IGWs are 0. So in this case, this problem reduced to a set of Laplacian equation. The decomposed results show that in the super inertial band, high mode IGW dominates, while in the sub inertial band, sub-mesoscale eddies are stronger. The exception lies around the diurnal band. The exception must due to our assumption here. So we try to impose some physical constraints. Divergence in spectral space, divergence must be greater than relative vorticity and smaller than this term. This inequality comes from the divergence equation. This inequality comes from vorticity equation. In this way, we can improve the result clearly around this band of diurnal tidal signal. Here we show the decomposed sub-mesoscale eddies and high mode IGWs after improvement. It seems quite encouraging. We hope that this method will apply to cases where signals of IGWs does not concentrate along dispersion relations regularly. Up to now, we have decomposed, we have separated different signals. Next, we will try to reconstruct the interior flow from decomposed sea surface height. For some mesoscale eddies and high mode IGWs, their vertical mode it's difficult to distinguish. So here we just focus on mesoscale eddies and low mode IGWs. For low mode IGWs at the surface, we will use the polarized relation to derive surface velocity. Here, the picture shows both its spatial pattern and the temporal evolution are consistent with targets very well. For submasses, for IGWs at the subsurface, we'll use the vertical normal mode will be used. Once again, the spatial pattern and the temporal evolution are quite well reproduced. For mesoscale eddies at the surface, geostrophic relations is used. Spatial pattern and temporal evolution are still very reproduced. For mesoscale eddies at the subsurface, we assume barotropic mode and the first Baroclinic mode dominant, and the bottom flows vanishes. And then with the help of vertical normal modes, we can reconstruct subsurface mesoscale eddy flow. The reconstruction remains good up to 50 meters, but it gets bad at 200 and 500 meters. Here we extract two moorings to argue that the common assumption is invalid, at least in South China Sea, although it applies well in the open ocean. Now we come to conclusion. We propose a robust and self-consistent technique to decompose different kinds of processes as accurately as possible. Particular efforts are made to disentangle high mode IGWs from submesoscale eddies. Lastly, submesoscale features are inferred from sea surface height. Thank you.
Thank you. So we have a bit of time for a few questions. Carsten.
In your frequency wave number diagram of the model, which has tidal forcing, I suppose, there's the tides I can see, the low mode tides, maybe first mode, second mode, but also superharmonics, right? Is this something some related to what Bruce said, that the tides are decomposing or decaying into superharmonics? Can you comment on that?
I think this is a good question. I have never thought about this question. In South China Sea, the surface harmonic tidal signal is very, very strong. Unlike the open ocean, I don't know how to answer your question related to the previous lecture.
Yeah, maybe you can conduct a model experiment where you, or I don't know, where to prove that this is actually due to superharmonics or generation by superharmonics. I don't know, maybe, but it's very interesting.
Thank you.
Can I ask a question too? So you're using very different methods to decompose, to isolate inertial gravity waves or to isolate the mesoscale. I guess there's no orthogonality. So I mean, some of the energy can go in the same energy can go in different categories with your method.
I don't think so. Since we decompose in the spectral space, there's no overlap in spectral space when we try to decompose them.
But for low mode inertial gravity waves, you are using the dispersion relation. You're also using the spectral space decomposition.
Yeah, at first in the spectral space we extract those bands off.
I see. Okay. Any other question? Apart from a congratulation to Carsten by Bruce for having spotted harmonics. Okay, well, thank you very much. So that we are almost on time for the next talk, which will be recorded, I'm told. Everything is a bit recorded, but this one will be doubly recorded. So if you don't want to be seen twice, switch off your camera. So the next talk is by Kevin Lam. Are you around, Kevin?
I am.
Good, good. So you can share your screen and go ahead, and you have 30 minutes, well, 25 minutes.
Sorry.
We don't want to see your code.
No, probably not. How's that? Can you hear me?
Yes, we can. Yeah, that's
Yeah.
good.
Okay. So I'm going to talk today about some work on internal wave generation by tidal currents at supercritical latitudes. So first of all, just a little bit about the numerical model. So the numerical model, which is freely available to anyone who's interested, has a number of approximations. So it's a two-dimensional model, so independent of flow along in the y direction. And it has a rigid lid, which is important for tide topography interactions, especially with shelf topography, because the horizontal volume flux, right, is going to be independent of the horizontal location. So you can't, for example, model, say, damped tidal waves propagating over a shelf. It uses a structured quadrilateral grid, so you can vary the vertical resolution, which is important in this case because there's a very thin pycnocline up near the surface. And so in order to resolve that, we've got stronger resolution in the upper region. Okay, so today I'm going to talk specifically about an investigation of internal wave generation on the Urmac Plateau. So this is work with Gavin Urbanchik, Ilker Fair, and Laurie Padman. So this map shows you the location of the Urmac Plateau. So in particular, the Urmac Plateau is between about 80 and 83 degrees north, which is north of the critical latitudes for M2 and, well, obviously diurnal tides as well. So if you recall the internal wave dispersion relation for internal plane waves on an F plane, right here it is. So assuming F squared is less than N squared, then the frequency for freely propagating internal waves must lie between F and N. So in particular, no freely propagating waves with frequencies below F. And for Coriolis frequencies, so the Coriolis frequency is equal to the semi-diurnal M2 tide at 74.5 degrees north and K1 at 30 degrees north. So the Urmac Plateau is a bit north of the critical latitude of the M2 tide and well north of the critical latitude for the K1 tide. But as we'll see, there can be lots of waves generated by the K1 tide. So this work is motivated by some observations that show strong cross-shelf diurnal currents, which are believed to be associated with near-resonant diurnal shelf waves propagating anti-clockwise around the plateau. So the K1 tides are much stronger than the M2 tides, although they're not, I guess, maybe strictly speaking, tidal currents, because they're associated with these shelf waves. And the diurnal tide is believed to be at least indirectly responsible for amplification of diapycnal mixing rates over the plateau slope, as well as acting as a heat pump through the surface mix layer. So our focus is on the diurnal tide and the generation of internal solitary waves, but I'm going to also show results for the M2 tide. So the generation of internal solitary waves at high latitudes has been studied numerically before, but only for the M2 tide. So for example, Lysenko et al. Looked at internal solitary wave generation in the Barents Sea. They were close to and slightly north of the critical latitude for the M2 tides, but they reduced F to that for a latitude south of their location due to the effects of background mean currents. So then in their situation, they were no longer at supercritical latitudes. Reipeth et al. Looked at wave generation in Spitsbergen Bank, and in this case, so Vlasenko was also one of the co-authors. In this case, they didn't reduce F, so they did look at the generation of internal solitary waves at supercritical latitudes for the M2 tide. And then in another paper, Kurkina and Talipova looked at generation at 78.5 north. There are several observations of internal solitary waves and high frequency internal waves at high latitudes, although not a huge number. So SAR images, and in of particular interest here, Zipod et al. Saw packets of internal waves riding on the crest of a diurnal internal bore. This is under the ice in April, and that was part of the Cirex experiment along the northern Yermak Plateau. And I meant to mention, so if I go back here, you can see the red line in the right panel. So that's our north transect. So that's the bathymetry we're using. And this is where these strong nonlinear waves were generated. We also did experiments or numerical simulations along a southern transect, which I'm not going to show any results for because no internal solitary waves in that case. But most of the simulations use a latitude of 80.8 north that's associated with the southern transect and not the northern transect. But F doesn't vary very much, and so the results aren't very sensitive to the difference in F. So just a bit about the model setup. So F is usually value for 80.9 degrees north, but have done a number of other latitudes, and I'll show some results from some other latitudes. The left plot shows the vertical resolution in the shallow and deep water. So it uses a sigma coordinate, so the same number of grid cells in the vertical in both shallow and deep water. So a higher resolution in the shallow water than there is in the deep water. So you can see in the upper few hundred meters, right, our resolution, vertical resolution is, order a couple of meters. The lower plot shows the horizontal resolution for the bulk of the simulation. So again, it uses a horizontally varying grid. So in this case, resolution of about 30 meters in the central region, and then it gets stretched as you go towards the boundaries to avoid reflection of internal waves off the boundaries. And this dashed line indicates the shelf bathymetry. So you can see we've got high resolution over the shelf slope and then to either side of the shelf. So the M2 tidal simulations use a maximum current of, or a tidal current of 1.4 centimeters per second in the deep water, which is 3,800 meters deep. And that translates to a current of 6.9 centimeters per second on the shelf, which is 774 meters deep. So on shelf, it's still quite deep. For the K1 tide, we've used a range of currents, so ranging between 2.3 centimeters per second and 23 centimeters per second in the deep water. And that translates between 0.11 and 1.1 meters per second on the shelf. And here's the stratification. So left panel is the density, right panel is the buoyancy frequency. So this is based on an observed profile, so it's not based on climatology. Climatology, you tend to get a wider picnic line, right? So it's less well-defined and lower peak values of N. Okay, so internal wave characteristics in a vertically varying stratification are given by, so this equation here just comes from the dispersion relation, right? So k squared over m, you can write the dispersion relation for plane waves in this way, k squared over m squared, right? Omega squared minus f squared over n squared minus omega squared. Now if n is a function of z, right, you get energy propagating vertically along these characteristics with slopes given by dz by dx. So z, integrate this, you get z of x, and that gives you the characteristic. Okay, so in the plots, I'll show some of the wave fields, and I'll superimpose some of the characteristics. Okay, and so here's the first example. So this is the weak M2 tide, so it's very linear. This plot, the colors show the baroclinic velocity after 50 tidal periods, right? So red are positive values, blue are negative values. And the black curves are characteristics for a frequency of 1.0 times the M2 tidal frequency. Okay, so you can see beams of this frequency radiating away from the shelf, well, particularly onto the shelf. Okay, even though the forcing frequency M2 is less than F. So in these beams, the maximum horizontal current is about 0.5 centimeters a second. So they're quite weak. The lower panel, it's the same plot of the baroclinic horizontal velocity field. The characteristic is different. It's for a slope, or sorry, a frequency of 1.07 times the M2 tidal frequency. And if you look, you can see that the characteristic has a slightly higher slope, okay, and it sort of follows the beam quite well here, but this characteristic follows the lower part of the beam. So the beam is comprised of a range of frequencies. This compares results at two different latitudes. So the upper panel is at 80.9 north, so exactly the same as this lower plot here, right? And the lower panel is at 86 degrees north. Okay, so a little sort of extreme example, but as you can see, the results are very, very similar. Okay, so the results aren't very sensitive to F at these latitudes or to changes in latitude. Here is an example for a weak K1 tide at again 80.9 north and again at 50 tidal periods. And here I'm plotting the frequency for twice the K1 tidal frequency. Okay, so you can clearly see beams emanating away from near the top of the shelf of twice tidal frequency. So next, I'm going to talk about the frequencies for which the slope is critical. And as you can tell, for example, from this plot, right, the slope is critical at the very top of the slope near the shelf break. That is, the slope of the bathymetry is equal to the slope of, you know, internal wave or plane waves, internal wave beams of frequency 2 omega K1. So you've got strong generation at this slope, or this location where the slope is critical. So linear theories for internal wave generation by tide topography interaction predict the generation of all harmonics of the tidal, or of the forcing frequency, well, within the allowed range F over N. But Nakamura et al. In 2000 argued that for strong tidal currents, the effects of advection should be taken into account, predicting that waves with frequencies plus or minus the forcing frequency minus UK are generated. Right, so here U is the current speed, K is the horizontal wave number of the forcing, which comes from the Fourier transform of the bottom barotropic current, and well, sigma F is the forcing frequency. So there are sort of three regimes. You've got the internal tide regime where UK is much less than the forcing frequency, and then you're just generating waves of tidal frequency propagating in both directions. At the other extreme, the forcing frequency is very weak and you're generating waves of frequency UK. And these are just Lie waves, right? So you have flow, think of flow over sinusoidal bathymetry with some wave number K, right? And you're going to generate waves whose phase speed is equal to the current speed U, and they'll have wave number K and they'll have frequency UK. And then there's the mixed tidal Lie wave regime where UK over sigma F are order 1. Okay, so this plot shows the frequencies for which the slope is critical. So the y-axis is the vertical, right? And then frequency is along the horizontal axis. And so this red curve is at 80.9 degree north. And so given a depth, say Z is -2 kilometers, right? This tells you what frequency is critical at that depth. Okay, and these vertical dashed lines are frequencies 1.03 times the M2 tidal frequency up to 1.08 times the M2 tidal frequency. So what this shows is that the slope is critical to frequencies ranging between approximately 1.03 omega m2 and 1.08 omega m2. And at 82.2 degrees north, because that's the actual location of the north transect, right, it's very similar. So what this means is you can potentially have strong generation for frequencies between 1.03 omega m2 and 1.08 omega m2. And that's what you see in, these plots, okay? And this vertical dashed line here is twice the diurnal tidal frequency. So this bathymetry has critical slopes for a narrow range of frequencies. It includes the range of frequencies for which you see beams for the M2 tidal frequency, and it includes twice the diurnal tidal frequency. So here are some dispersion curves. So up here, just showing the phase speed in the solid curves and the group velocity in the dashed curves for modes 1 to 3. These symbols indicate frequencies as indicated over here. So down here, right, the dots, that's for twice the tidal frequency, and these diamonds are for 1.07 times omega m2. This lower plot shows the group velocity as a function of the frequency, and again for a few vertical dashed lines for a few select frequencies. And from this, you can work out how far the energy propagates in X number of tidal periods. And so in those plots I showed you after 50 tidal periods, right, there's ample time for all of these modes to arrive, even for omega or twice omega k1. Also note that the largest group velocities are for much longer or much higher values of k. Okay, so much higher frequencies than are being generated. Okay, so then we've got this hypothesis then that wave beams are formed due to resonant forcing of mixed tidal Lie waves. And if we use the peak on shelf current of 0.069 meters per second, then omega m2 plus UK is 1.0 omega m2 for a wavelength of about 44 kilometers. We get 1.05 omega m2 for a wavelength of about 62 kilometers. And these are comparable to the cross-shelf distance of about 80 kilometers. Okay, so our hypothesis is that this is the mechanism by which these beams are being formed. Okay, so now I'm going to show an animation of, okay, this is not a waterfall plot. So I'm going to show an animation of just the evolution or the time evolution of an isopycnal that's at 50 meters depth. So it's just below the picnic line. And this is for the weak tidal currents. And so over this region between say 50 and 80 kilometers, what you're seeing is just the up and down heaving of the isopycnal by the tidal currents. Okay, and that's where the largest vertical displacements take place. Initially, you can see some sort of larger waves radiating away. So these are early transients, and then the radiating waves decay in amplitude as time goes on. So to look at this in another way, here's a waterfall plot. So each curve then shows that isopycnal at different times, right? So they're all offset a little bit. So in the central region, so the time along here, so this is after 1, 2, 3, etc. tidal periods. So K1 tidal periods, you can see the up and down heaving of the isopycnal over the shelf, and then these radiating waves. Now, if we look at this blue sloping line to the right, so this is, think of a point moving with the maximum group velocity for mode 1 waves. Okay, and that's a frequency of, I forgot, something like 6 times the tidal frequency. And the green curve, maximum group velocity for mode 2 waves. These orange and red curves are the wavefronts for mode 1 and 2 waves with twice the tidal frequency. So you can see this strong emission of waves from the so I forgot to mention, so the simulations are started impulsively with maximum on-shelf currents. So you get this wave front of mode 1 waves propagating to the right, and then in the deep water, it's primarily mode 2 waves. Here now we look at a strong tidal current. So the tidal current is 10 times stronger. And now the results are very different. Okay, so you can see this strong or the generation of these internal solitary wave packets. And here's the waterfall plot corresponding to that case. So compared to this case, right, the scaling of the, the ice spignals is much different. So here you can see the vertical motion over the slope. And for this case, the current's 10 times stronger. So that vertical heaving over the slope is actually 10 times larger. So I've had to scale everything down so they don't overlap. So the scaling is, so these waves are about 100 times larger than in the other case. But what you can see are these packets of waves, solitary waves, propagating in both directions. And if we look, say, early on here, you can see a leading solitary wave propagating to the right, and then trailing that, there's a packet of solitary waves. And then not so much in the first couple of tidal periods, but later on propagating to the left, you can see, say, a single solitary wave, and then often a packet of solitary waves. So there's sort of two sets of waves emitted going to the right and two to the left every tidal period. Here I'm just comparing the that same isopignal at 50 meters depth, and here so the red is that from the results I just showed you with the strong tidal currents, and the blue is just for a simulation run without gravity. So here it's just showing how that isopignal gets moved up and down by the barotropic tidal currents. So no emitted, no internal waves in this case. So after a quarter of a tidal period, right, you can see without any gravitational restoring forces, right, the isopignal is just being raised. We're now at the end of on-shelf flow since we started at maximum on-shelf flow. Whereas gravitational restoring forces, right, have started to pull down the isopignal in the middle of this sort of elevation. And then this is an eighth of a tidal period later, and this is after half a tidal period. So now you've at the, so you've gone, you start at maximum on-shelf flow. So at half a tidal period, you're at maximum off-shelf flow. And in the no gravity case, the isopignal has just returned to its rest height. And this is actually why the simulations are initialized like this, so that the mean height of the isopignal is roughly 0. Okay, but you can now see after half a tidal period, there's two sort of depressions in the case with gravity, and in the middle, right, the isopignals are being drawn down by the off-shelf flow, and later on, right, you can see this is developed. So there are now two depressions sort of going to the right, and there are two going to the left, and this is what gives rise to the two sets of internal solitary waves. Okay, so here you can see them evolving at later times. Okay, so just some comparisons. So this case is a very strong tidal current case. So if we vary the current, so at the top, this is so results after 3 tidal periods, so 0.23 meters per second, our strongest current, and then 80% of that, 70%, and 60, 70, 80% of that current. Okay, so you can see, obviously, as should be obviously expected, right, as you reduce the current, right, the amplitude of the internal solitary waves goes down, and then they disappear at a bit under 0.138 meters per second. So this just compares results at 2 different latitudes at 80.9 and 82.2 for the strong tidal current case. So after 2 tidal periods, the results are indistinguishable. And after 4, you can see that there's a little bit of a difference. Okay, so again, to the fact that the results are not very sensitive to F. Now, I've pointed out that those, because of the impulsive start, you get these high frequency waves propagating off to the left and right, on shelf and off shelf. So we've done some simulations using ramping up the tidal currents. So the upper two panels, this is from a run with the impulsive startup after 2 and 4 tidal periods. And then the lower panel, we ramped up the tidal currents over over 4 tidal periods. And then this is the results 2 tidal periods later and 4 tidal periods later. So you can see that the results are pretty repeatable from one tidal period to another, and not very sensitive to the impulsive startup, really. So, and that's it. Questions?
Thank you very much. So do we have questions? So I'll get going actually. Is there a sort of way of predicting how many solitary waves you're going to get depending on flow strength and slope? Is there some simple model one can devise for that?
No, not in situations like this. I mean, there are models if you start from, like if you've got the KdV equation and you start with some initial shape, then there are theories for predicting the number then. But for cases like this, none that I know of.
There's nothing even sort of qualitative based on conservation of mass and momentum or something? There's no...
Not that I'm aware of.
So you have to run the full thing every time. Okay, Carsten, you have a question?
In this case, which was a little bit simpler, the one with the weaker flow, there were no solitary waves, but there was this higher frequency, right? The superharmonic with I think 6 tidal frequency or 6 times tidal frequency. How does that come along actually, these fast waves?
Well, sorry, I'm trying to find here.
Yeah.
Well, it's really from an impulsive startup. I mean, right? If you think of taking Laplace transform, right? You've got some 0 state, and then you switch on some forcing. You force immediately all frequencies.
Okay.
So because of the impulsive startup, all frequencies are forced, and including waves with the frequency with the fastest group velocity, and so that's what you're seeing.
Okay, but I can also see them later on, the fast waves.
Sure, they're not.
So where do you see them?
In the upper part of the panel, there are still these phase lines faster than they should be.
Well, I mean, here, if you follow these, for example, I mean, the slope's not as steep as these, right? So these are these, yeah. Okay, think about it. I mean, I guess I'm not. Okay, I don't have a good answer for you.
That's what he wanted.
I mean, I think it's because you're going to generate waves of all frequencies. You'll have the fastest propagating waves here, right here, the say mode 1 waves of twice tidal frequency, and everywhere in between is going to be filled up with other waves. We haven't looked at decomposing these into the different frequencies to see what, say, the makeup of the waves over here is. So I'm not sure. But you also have to remember what you're seeing here is phase propagation and not energy propagation. So these, I'm showing you, these curves are the waves with the fastest group velocity, which is not the same as the fastest phase speed by any means. Yeah, I'd have to think more about that.
Okay, so Boris has a question or a comment.
Yeah, it was very interesting. I wanted to know, Kevin, if you tried to derive KdV equation for your solitons and maybe study their properties in the framework of this famous equation?
We have not done that. No.
All right. Well, if you have a chance, maybe you can look into it.
Yeah, I'm not. I think it would be a problem because the waves are generated by the way that the flow is forced up and down over the shelf slope. I imagine it would be tricky to model that. These solitary waves are also quite strongly affected by rotation, which is a further complicating factor. But I mean, there are KDV type models that include rotational effects.
But wouldn't you need
we've not thought of doing
slope?
Pardon me?
You probably would need also small slopes, right, for KDV like.
You mean bathymetry slopes?
Yeah.
Yes, you would. I mean, the environments they're propagating in would have to vary slowly compared to their length scale, which, I mean, that's probably fairly reasonable. I mean, the slope bathymetry is between about 0 and 80 kilometers, right? So it's a very long length scale compared to the length scale of individual waves. So it might be okay.
Okay, so there's a question in the chat by Jinsong von Storch about the implication for mixing of this.
Yeah, I was wondering how these solitons will affect mixing. I mean, the tidal mixing has been parameterized in various schemes, and also, but this type of thing they didn't consider. So the question is,
so as I mentioned early on, observations have shown enhanced vertical diffusivity associated with these waves. So one possibility is, I mean, the picocline is quite thin, right? So you'll get strong shear across the picocline associated with the internal solitary waves, which will, can be unstable. Haven't looked into that. But that's the mechanism by which internal solitary waves usually produce mixing is through, triggering shear instabilities.
And also, I mean, how widespread is that? Can we observe that? I mean, for M2, for K1, that's already, we have critical level at 30 degrees. So there are big areas where, can we say that there's lots of places where we can have this type of solitons?
At these latitudes,
yeah,
probably not. Certainly at lower latitudes, I mean, they're commonly observed in a lot of places. So one thing I didn't get into, I mentioned, all of these results are from that north transect. And you do not see internal solitary wave generation at the southern transect, even though at that location, the shallow water is actually shallower, meaning you could expect stronger currents. But the bathymetry is a bit wider. Okay, so, because the bathymetry is wider, and we look at this, the way the isopicals get pushed up and down over the slope, I mean, is, over a much longer region. So the left and right flanks of this elevation and depression from the tidal heaving have much weaker slopes. And so they don't nonlinearly evolve into internal solitary waves. And the other special thing about the Yermak Plateau is these strong diurnal currents, right, associated with these shelf waves. And so I think it's probably a fairly unique location.
Okay.
Okay, if there are no other questions, I think we can conclude this session. I'm not quite sure what the discussion session was planned to be, whether it was here or in Gathertown.
We can have it at both places. So people.
Both places is not so good when people don't switch off their microphones.
Yeah, don't know who goes where.
The idea was to make this a part of the meeting, so general discussion, also the questions that were probably not addressed during the talks, and then we can go to Gather Town. But if they are
Okay,
there,
so we can just ask whether anybody has questions about any of the talks.
yeah, or yeah, anything related.
Is my screen still being shared?
Yes.
Yes.
Right. So I can't seem to stop it.
Well, you have to give another talk then.
Oh, okay, sorry, got it.
Yeah, so I mean, if there are no further questions about the talks, we might do this informally in the scenery of Gather Town.
Okay. But if you leave Zoom, or if you don't leave Zoom, then you should put this leave computer audio button. So maybe Jack, you can explain this better than
Yes,
me.
so if you go, there's a button for mute. If you click on the arrow just near it, you select audio settings, I guess. Oh no, leave computer audio. Yeah, and that will switch off the computer audio. Also, something I was told earlier today, is that in Gather Town, if you go on the carpet, then you only listen to people on the carpet, which is a good tip if you don't want to have too much background noise to have a specific conversation.
If there are no more questions from the side of YouTube or the Slido thing, I think we can also close the streaming then.
We should pause the streaming now, and
I will do that.
And I don't know, we can still continue discussing here if anybody is interested. Anything cross-questioning or anything that was not addressed before. If you want to move to Gather Town, then we can